ये है थर्मल प्रॉपर्टी ऑफ द मैटर। तो पहले इसका कुछ पीवाईक्यू देख लेते हैं और फिर उसके बाद इसका देखेंगे हम लोग एनसीईआरटी। तो पहला क्वेश्चन इसमें जो आया था वो था कि एक कॉपर रॉड of the 88 centimeter and aluminum rod of the unknown length have their increase in the length independent of increase in temperature। तो लेंथ ऑफ द एल्यूमिनियम रॉड है जो कितना हो जाएगा, तो हम जानते हैं कि ड्यू टू चेंज इन टेम्परेचर द थर्मल स्ट्रेंथ प्रोड्यूस्ड फ्रॉम द रॉड ऑफ द लेंथ एल गिवन बाय डेल्टा एल बाई एल हो जाता है अल्फा डेल्टा टी। तो डेल्टा एल कितना हो जाएगा, डेल्टा एल हो जाएगा एल अल्फा डेल्टा टी, वेयर एल इज द ऑर्डिनल लेंथ ऑफ द रॉड एंड अल्फा जो कोफिशिएंट ऑफ द लीनियर एक्सपेंशन ऑफ द फुल रॉड है। तो द लेंथ चेंज इन द length delta L of the given two rods of the copper and aluminum are independent of the temperature change. That means delta T is same for both copper and aluminum. तो एल सी अल्फा सी इक्वल टू होता है एल अल्फा सी इक्वल टू 1.7 पर केल्विन है और अल्फा एल जो है 2.2 पर केल्विन है। अल्फा एल सी जो है 88 सेंटीमीटर है। तो एल हो जाएगा एल फ्यू अल्फा फ्यू बाई अल्फा एल, तो आ जाएगा कितना 58 सेंटीमीटर। तो इसका आंसर कितना जाएगा, ऑप्शन सी 58 सेंटीमीटर। नेक्स्ट है कि कोफिशिएंट ऑफ द लीनियर एक्सपेंशन ऑफ द ग्राफ एंड द स्टील रॉड फॉर अल्फा 1 एंड अल्फा 2, length of the brass and the steel rod for the L1 and L2 respectively. If L2 minus L1 is maintained at the same at all temperature, which one of the following relation holds good? तो कोफिशिएंट ऑफ द लीनियर एक्सपेंशन ऑफ द ब्राफ हो जाएगा अल्फा 1, कोफिशिएंट ऑफ द लीनियर एक्सपेंशन ऑफ द स्टील हो जाएगा अल्फा 2, लेंथ ऑफ द ब्राफ एंड द स्टील रॉड फॉर L1 and L2 respectively. As the given difference increase in the length L2 dash minus L1 dash is same for all the temperature, so L2 dash minus L1 dash equal to L2 minus L1. तो L2 1 प्लस अल्फा 2 डेल्टा टी माइनस L1 1 प्लस अल्फा 1 डेल्टा टी इक्वल टू L2 माइनस L1। तो L1 अल्फा 1 इक्वल टू हो जाएगा L2 अल्फा 2, तो आंसर आएगा ऑप्शन सी L1 अल्फा 1 इक्वल टू L2 अल्फा 2। नेक्स्ट है कि द वैल्यू ऑफ द कोफिशिएंट ऑफ द वॉल्यूम एक्सपेंशन ऑफ द ग्लिसरीन इज 5 - 4 पर केल्विन। तो द फ्रैक्शनल change in the density of the glycerin for a rise of the 40 डिग्री सेल्सियस in the temperature कितना हो जाएगा। तो गिवन द वैल्यू ऑफ द कोफिशिएंट ऑफ द वॉल्यूम एक्सपेंशन ऑफ द ग्लिसरीन जो है 5 - 4 पर केल्विन दिए हुए। And the ordinal density of the glycerin rho is equal to rho naught 1 plus alpha gamma delta t, रो माइनस रो नोट हो जाएगा रो नोट गामा डेल्टा टी। Thus the fractional change in the density of the glycerin for rise of the 40 degree Celsius temperature हो जाएगा रो माइनस रो नोट बाय रो नोट इक्वल टू गामा डेल्टा टी। तो 5 - 4 - 4 - 40 यानी कितना आ जाएगा 0.020। इसका आंसर कितना जाएगा, इसका आंसर होगा ऑप्शन बी 0.020। फिर आता है on the new scale of the temperature which is linear and call a W scale, the freezing and the boiling point of the water 39 degree watt and 240 degree watt respectively. So what will the temperature on the new scale corresponding to the temperature of the 39 degree Celsius on the Celsius scale? तो हम जानते हैं कि the relation between the true scale and the new scale of the temperature given by T minus L of P by UFP minus L of P true equal to T minus L of P by UFP minus L of P faulty। तो 39 माइनस 0 बाई 4 माइनस 0 इक्वल टू टी माइनस 39 का 39 माइनस 239 माइनस 39 तो कितना जाएगा टी इक्वल टू 117 डिग्री वाट। तो आंसर आएगा ऑप्शन बी 117 डिग्री वाट। नेक्स्ट है कि द कोफिशिएंट ऑफ द लीनियर एक्सपेंशन ऑफ द ब्रास एंड ऑफ स्टील अल्फा 1 एंड अल्फा 2 respectively when we take a brass rod of the length L1 and a steel rod of the length L2 at 0 degree Celsius, then the difference in the length L2 minus L1 will remain the same at all temperature। तो इसमें हो जाएगा कि कोफिशिएंट ऑफ लीनियर एक्सपेंशन इज इक्वल टू होता है चेंज इन द लेंथ बाय ऑर्डिनल लेंथ गुना राइज इन टेम्परेचर। तो अल्फा इज इक्वल टू डेल्टा एल बाई डेल्टा टी यानी डेल्टा इज इक्वल टू एल अल्फा टी। तो फॉर ब्रास रॉड डेल्टा एल वन इज इक्वल टू एल वन अल्फा टी वन, फॉर स्टील रॉड डेल्टा एल टू अल्फा टू टी। तो एल टू माइनस एल वन इज इक्वल टू हो जाएगा कॉन्स्टेंट। तो डेल्टा एल टू माइनस डेल्टा एल वन इज इक्वल टू जीरो। तो डेल्टा एल टू इज इक्वल टू डेल्टा एल वन यानी एल टू अल्फा टू टी इज इक्वल टू एल वन अल्फा वन टी। तो L2 अल्फा टू इक्वल टू क्या आता है L1 अल्फा 1। इसका आंसर क्या आ जाएगा, इसका आंसर आएगा ऑप्शन नंबर बी। इसका आंसर आएगा ऑप्शन है कि L1 अल्फा 1 इक्वल टू L2 अल्फा 2। नेक्स्ट है कि मरकरी थर्मोमीटर कैन बी यूज्ड टू मेजर द टेम्परेचर अप टू द आंसर आएगा ऑप्शन सी कि मरकरी थर्मो पहले से पूछा था कि मरकरी थर्मोमीटर इज लिक्विड थर्मोमीटर एंड इट इज बेस्ड अपॉन द यूनिफॉर्म वेरिएशन इन द वॉल्यूम ऑफ द लिक्विड विद हाई टेम्परेचर। Mercury is opaque and bright and therefore can be easily seen in a glass tube, and it is a good conductor of the heat and the temperature of the both hot but quickly. A mercury thermometer can be used to measure the thermometer of the 10 degrees Celsius or so before boiling at 357 degrees Celsius. The vaporization of mercury will start। फिर आता है A centigrade and the Fahrenheit thermometer are dipped in the boiling water. The water temperature is lower until the Fahrenheit temperature is lifted up 140 degree. The water is fall in the temperature at the centigrade lifted by the centigrade thermometer. The relation between the Celsius and the Fahrenheit scale C by 4 is equal to the F minus 35 180. तो C by 4 is equal to 140 minus 35 of यानी 0.6. C is equal to आ जाएगा 50 डिग्री. Hence fall in the temperature is equal to temperature of the boiling point, boiling water minus final temperature यानी क्या जाएगा कितना 40 डिग्री. तो आंसर है ऑप्शन सी 40 डिग्री. नेक्स्ट है कि द क्वांटिटी ऑफ द हीट रिक्वायर्ड टू रेज द टेम्परेचर ऑफ द टू सॉलिड्स कॉपर ऑफ पेयर ऑफ द रेड है R1 and R2 where R1 is equal to 1.5 R2 so the 1 Kelvin are in a ratio. तो since the heat required Q is equal to mc delta T तो 4/3 pi R Q into rho is equal to C delta T जहाँ m जो है V of पेयर into rho हो जाएगा. तो since pi rho C and T are constant तो Q डायरेक्टली प्रोपोर्शनल टू RQ तो Q1 by Q2 जो हो जाएगा R1 by R2 का होल Q. तो R1 by R2 का होल Q तो 1.5 R2 by R2 यानी 21/8 इसका आंसर आएगा. तो इसका आंसर ऑप्शन डी 21/8. नेक्स्ट है A piece of the ice falls from a height edge so that it melts completely. Only 1/4 of the heat produced is absorbed by the ice and all energy of the ice gets converted into the heat during its fall. The value of the H is the latent heat of ice due at 3.4 joule per kg और G due at Newton per kg. So according to the question, the conservation of energy gained by the ice during its fall from the height edge is equal to mgh. As given, only 1/4 of its energy is absorbed by the ice. तो mgh by 4 is equal to ml. तो l h is equal to हो जाएगा mlf into 4 by mg. यहाँ से करेंगे तो कितना आएगा 136 किलोमीटर. तो आंसर आएगा ऑप्शन बी 136 किलोमीटर. Next, two identical bodies are made up of a material for which the heat capacity increases with temperature. One of these is at 4 degrees Celsius while the other is at 0 degrees Celsius. If the two bodies are brought into the contact, then assuming no heat loss, the final common temperature कितना हो जाएगा तो more than the 50 degrees Celsius. Heat lost by the first body is equal to heat gained by the second body. So body at 4 degrees Celsius temperature has greater heat capacity than body at 0 degrees Celsius. So the final temperature will closer to the 4 degrees Celsius if electricity जो होगा 50 degrees Celsius से ज़्यादा हो जाएगा. अगला सवाल, if steam of at the 4 degrees Celsius is passed into the 20 gram of the water at 10 degrees Celsius, when water acquires a temperature of 80 degrees Celsius, the mass of the water present will be take a specific heat of the water 1 calorie per gram per degree Celsius and latent heat of the steam 540 calorie per gram. तो हम प्रिंसिपल ऑफ द कैलोरीमेट्री करेंगे तो हीट लॉस्ट बाय द स्टीम इज इक्वल टू हीट गेन बाय द एम डैश विद द अमाउंट ऑफ द स्टीम दैट कन्वर्ट्स इनटू वाटर. तो एम डैश इनटू एल इज इक्वल टू हो जाएगा एम डैश एफ डेल्टा टी यानी एम एफ डेल्टा टी. तो एम डैश इंटू 540 प्लस एम डैश इंटू 1 इंटू 4 माइनस ऑफ इक्वल टू 20 गुना 1 गुना 80 माइनस 10. तो एम डैश इक्वल टू कितना आएगा 2.5 ग्राम. तो नेट मास ऑफ द वाटर आ जाएगा 25 20 प्लस 2.5 यानी 22.5 ग्राम. तो आंसर ऑप्शन डी 22.5 ग्राम. फिर एक लिक्विड ऑक्सीजन at 50 Kelvin is heated to 200 Kelvin at constant pressure of 1 atm. The rate of the heating is constant. Which one of the following graph represent the variation of the temperature with time? तो आंसर है ऑप्शन ए. आंसर है ऑप्शन ए. ये है जो वेरिएशन ऑफ टेम्परेचर विद टाइम दिखा रहा है. ग्राफ इज शो द वेरिएशन ऑफ द टेम्परेचर विद टाइम. एज फर्स्ट टेम्परेचर विल इंक्रीज देन देयर विल बी स्टेट चेंज फ्रॉम द लिक्विड टू द गैस. फिर आता है कि when 1 kg of the ice at 0 degrees Celsius melts the water at 0 degrees Celsius, the resulting change in the entropy taking latent heat of the ice to the 80 calorie per degree Celsius is the change in the entropy given by delta is equal to ml by t यानी 1000 गुना 80 by 273 यानी 293 कैलोरी पर केल्विन. आंसर आएगा 293 कैलोरी पर केल्विन ऑप्शन सी. फिर आता है if 1 gram of the steam is mixed with 1 gram of the ice, then the resultant temperature of the mixture is the heat required by 1 gram of the ice at 0 degrees Celsius to melt into 1 gram of water at 0 degrees Celsius. Q1 is equal to ml to L यानी 1 into 80 यानी 80 कैलोरी. तो L is equal to कितना हो जाएगा 80 कैलोरी पर ग्राम. Heat required to by the 1 gram of water at 0 degrees Celsius to boil at 4 degrees Celsius. तो Q2 is equal to mc delta theta यानी आ जाएगा 4 कैलोरी. Thus the total heat required by the 1 kg of the ice to reach a temperature of the 4 degrees Celsius to Q is equal to Q1 plus Q2 यानी 80 plus 4 is equal to F calorie. Heat available with 1 gram of the steam to condense into 1 gram of the water at 4 degrees Celsius जाएगा Q def equal to ml def यानी L def latent heat of evaporation है. तो 1 गुना 536 कैलोरी यानी 536 कैलोरी हो जाएगा. तो obviously the whole steam will not be condensed and ice will attain temperature of 4 degrees Celsius. Therefore the temperature of the mixture is 4 degree Celsius हो जाएगा. तो इसका आंसर कितना जाएगा इसका आंसर आएगा ऑप्शन सी 4 डिग्री सेल्सियस. फिर आता है कि थर्मल कैपेसिटी ऑफ 40 ग्राम ऑफ द एल्युमिनियम F इक्वल टू 0.2 कैलोरी पर ग्राम केल्विन इज. तो thermal capacity of a body is defined as the amount of the heat required to raise the temperature of the whole body through the 1 degree Celsius or 1 Kelvin. Amount of the heat energy required to raise the temperature of the mass m of a body through the temperature range delta T delta Q is equal to m delta T varies with the specific heat of the body. When delta T is equal to 1 Kelvin, delta Q is equal to thermal capacity. So thermal capacity is equal to m into F. So m is equal to 40 gram, F is equal to 0.2 calorie per gram Kelvin. तो थर्मल कैपेसिटी हो जाएगा 40 गुना 0.2 यानी 8 कैलोरी पर डिग्री सेल्सियस. तो 4.2 गुना 8 यानी कितना जाएगा 33.6 जूल पर डिग्री सेल्सियस. आंसर आएगा ऑप्शन डी. फिर आता है कि two containers A and B are partially filled with butter and cooled. The volume of A is twice that of the B and it contains half the volume of the butter in B. If both are the same temperature in butter vapor in the containers will have the pressure of the ratio. The vapor pressure of a substance is independent of the amount of the substance. It depends only on the temperature. So they have the ratio of कितना 1:1. Answer option B 1:1. Next है 10 gram of the ice cube at 0 degree Celsius are diluted into a tumbler. Water equivalent 55 gram at 40 degree Celsius. Assuming that negligible heat is taken from the surrounding, the temperature of the water in the tumbler becomes nearly. So let theta be the temperature when thermal equilibrium has reached. Heat gained by the ice to be converted to the water at 0 degree Celsius, theta degree Celsius, ml plus mf थीटा माइनस 0. तो आ जाएगा 10 गुना 80 प्लस 10 गुना 1 गुना थीटा. तो हीट लॉस्ट बाय द टम्बलर एंड इस कंटेंट हो जाएगा 55 गुना 40 माइनस थीटा. तो यहाँ से आंसर कितना आ जाएगा. आंसर आएगा ऑप्शन. और अगर निकालेंगे तो आ जाएगा यूजिंग प्रूफ ऑफ द कैलोरीमेट्री दैट हीट गेन इक्वल टू हीट लॉस्ट 10 गुना 80 प्लस 10 गुना 1 गुना थीटा इक्वल टू 55 गुना 40 माइनस थीटा. तो थीटा कितना आ जाएगा 22 डिग्री सेल्सियस. तो आंसर कितना आ जाएगा. आंसर आएगा ऑप्शन बी 22 डिग्री सेल्सियस. फिर आता है a cup of the coffee cools from 90 degrees Celsius to 80 degrees Celsius in 30 minutes when the room temperature is 50 degrees Celsius. The time taken by the similar cup of the coffee to cool from 80 degrees Celsius to 5 degrees Celsius at the room temperature when same at 50 degrees Celsius is. तो रेशियो ले लेंगे इसमें न्यूटन्स लॉ ऑफ कूलिंग पर दिया हुआ है. तो इसी फ्लो उसमें हट चुका है. dt/dt होता है कि T1 यहाँ पर एवरेज लेते हैं माइनस T0. तो दोनों का रेशियो ले लेंगे. पहले के उसमें हो जाएगा 90 माइनस 80/t इज इक्वल टू के 90 प्लस 80/2 माइनस 20. ये पहला केस हो गया. फिर उसके बाद टी दिया हुआ था. फिर 80 माइनस 50/t1 इक्वल टू यहाँ से निकाल के रिप्लेस किया. बल्कि यहाँ पर रेशियो लेना चाहिए था. कट जाता के और आसानी से मेरा निकल जाता. आंसर इसका कितना आ रहा है. आंसर आएगा ऑप्शन बी 13/5t. आंसर आएगा 13/5t. Next, 3 stars A, B, C have the surface temperature TA, TB or TC respectively. Star A appear bluish, star B appears reddish and star C yellowish. Hence, तो लैम्डा जो होता है वो होता है B/T. तो लैम्डा इनवर्सली प्रोपोर्शनल टू T. वी नो दैट सबसे ज़्यादा होगा रेडिश का, फिर येलोइश का, फिर ब्लूइश का. तो सबसे ज़्यादा होगा TA, TC और फिर TB. तो यहाँ पर आता है ऑप्शन बी TA, TC और TB. फिर आता है कि an object kept in a large loom having a real temperature of the 25 degrees Celsius takes 12 minutes to cool from 80 degrees Celsius to 70 degrees Celsius. The time taken to cool for the same object from 70 degrees Celsius to 5 degrees Celsius कितना हो जाएगा. तो T1 माइनस T2 बाई T इज इक्वल टू 1/K T1 प्लस T2 बाई 2 माइनस T0. तो यहाँ से 80 माइनस 70 बाई 12 इज इक्वल टू 1/K 80 प्लस 70 बाई 2 माइनस 25. तो यहाँ से आ जाएगा इतना. फिर वही रेशियो लेना चाहिए था. तो कितना आ जाएगा 15 मिनट्स. तो इसका आंसर कितना आ जाएगा ऑप्शन डी 15 मिनट्स. फिर आता है कि deep rectangular pond of the surface area A containing water density rho of specific heat capacity F is located in a region where the outside air temperature is a steady value of at D minus 26 degrees Celsius. The thickness of the frozen ice layer in this pond at a certain instant is X. Taking the thermal conductivity of the ice as the K and its specific latent heat of the fusion as the L, the rate of the increase of the thickness of the ice layer at this instant would be given by. तो इसमें आता है कि डी थीटा बाई डी टी हो जाता है के थीटा नॉट माइनस थीटा 1/x. तो थीटा नॉट आ जाएगा रो ए डी एक्सएल और थीटा नॉट आ जाएगा 0. थीटा 1 आ जाएगा माइनस थीटा. तो थीटा नॉट इक्वल टू 0 डिग्री सेल्सियस. थीटा 1 इक्वल टू माइनस 26 डिग्री सेल्सियस. तो डी थीटा बाई डी टी आ जाएगा के थीटा नॉट माइनस थीटा 1/x यानी रो ए डी एक्सएल बाई डी टी यानी के थीटा नॉट माइनस थीटा 1/x. यहाँ कर सकते हैं कितना क्या है 26K बाई रो एक्सएल. तो इसका आंसर है ऑप्शन सी 26K बाई रो एक्सएल. Next है कि the power radiated by a black body is P and it radiates maximum energy at a wavelength lambda naught. If the temperature of the black body is now changed so that it radiates maximum energy at a wavelength 3/4 lambda naught, then the power radiated by it becomes NP. तो वैल्यू ऑफ द n कितना हो जाएगा. तो हम जानते हैं कि अबियंस लॉ भी है जो हट चुका है सिलेबस में. फिर भी देख लेते हैं छोटे छोटे टॉपिक्स. लैम्डा मैक्स इक्वल टू होता है T. तो लैम्डा मैक्स T1 इज इक्वल टू लैम्डा मैक्स इंटू T2, तो यहाँ से करेंगे तो कितना आएगा, लैम्डा मैक्स 2 इज इक्वल टू 3/4 लैम्डा नॉट, तो T1/T2 इज इक्वल टू 3/4 लैम्डा नॉट बाई लैम्डा नॉट यानी 3/4, तो T1/T2 कितना हो जाएगा 3/4। हम जानते हैं स्टीफन लॉ से कि पावर रेटेड बाय द बॉडी एट ए टेम्परेचर T गिवन बाय P इज इक्वल टू सिग्मा ए टी के पावर 4, तो सिग्मा रूट पी जो हो जाएगा डायरेक्टली प्रोपोर्शनल टू टी के पावर 4, तो P1/P2 इज इक्वल टू T1/T2 के पावर 4, तो P1/P2 इज इक्वल टू 81/256, तो P1 इज इक्वल टू पी, P2 इज इक्वल टू एन पी, तो एन इज इक्वल टू कितना आएगा 256/81, यानी कि आंसर आएगा क्या, आंसर आएगा ऑप्शन ए 256/81। नेक्स्ट है टू मटेरियल्स ए एंड बी आर ऑफ डिफरेंट मटेरियल्स are welded together as shown in the figure. Their thermal conductivity are K1 and the K2. The thermal conductivity of the composite rod कितना हो जाएगा, तो in the parallel arrangement of the n rods, equivalent thermal conductivity given by K equal to K1 A1 plus K2 A2 plus Kn by A1 plus A2 plus N. If the rods are of the same area, the Kn equivalent is equal to K1 plus K2 plus Kn by N. तो यहाँ से अगर निकालेंगे तो equivalent thermal conductivity of the system of two rods हो जाएगा K equal to K1 plus K2 by 2, तो आंसर आएगा ऑप्शन ए K1 plus K2 by 2। इसके बाद फिर आता है कि स्फेरिकल ब्लैक बॉडी विथ रेडियस ऑफ द 12 सेंटीमीटर, रेडियस 400 वाट पावर एट 500 केल्विन, इफ द रेडियस पर हाफेड एंड टेम्परेचर डबलेट, द पावर रेडिएटेड इन द वाट कितना हो जाएगा, तो रेडिएट पावर ऑफ ब्लैक बॉडी होता है P इक्वल टू सिग्मा टी के पावर 4, जहाँ सिग्मा ऑफ डिफरेंट कांस्टेंट है, T जो है टेम्परेचर ऑफ द बॉडी। तो when the radius of the sphere is halved, new area A def equal to A/4, तो पावर रेडिएटेड हो जाएगा P def इक्वल टू सिग्मा A/4 2T के पावर 4, कितना आ जाएगा 1800 वाट, तो आंसर पड़ेगा ऑप्शन डी 1800 वाट। फिर आता है कि black body is at temperature of the 5 Kelvin. The energy of the radiation emitted by the black body at the wavelength 5 nanometer is U1, at the wavelength 5 nanometer U2, and at 1 nanometer U3. Bn's constant B equal to 2.8 to the power 6 nm Kelvin. So which of the following is correct? The given temperature T1 is equal to 5 Kelvin. Since it is given that energy of the radiation emitted by the body at a high so nm is U1, at wavelength 500 nm is U2, and at 1000 nm is U3, तो lambda m into T equal to B, तो lambda m equal to B by T, तो lambda m equal to आ जाएगा 500 नैनोमीटर, तो lambda m जो होगा wavelength corresponding to the maximum energy, so U2 is कितना greater than हो जाएगा U1, तो इसका आंसर क्या आ जाएगा, इसका आंसर पड़ेगा ऑप्शन सी U2 is greater than U1। नेक्स्ट है कि a body cools from a temperature 382 in 10 minutes, the room temperature is T, assuming the Newton's law of the cooling is applicable, the temperature of the body at the end of the next 10 minutes कितना हो जाएगा, तो according to the Newton's law of the cooling, delta T is equal to delta T naught e के पावर माइनस लैम्डा टी, तो 3t minus 2t is equal to 3t minus t e के पावर माइनस लैम्डा इंटू 10, तो t डस माइनस t is equal to 2t गुना e के पावर माइनस लैम्डा इंटू 20, तो t डस माइनस t is equal to 2t e के पावर माइनस लैम्डा इंटू 10 बाई के स्क्वायर, तो यहाँ पर t डस इक्वल टू कितना आएगा 3t/2, तो आंसर पड़ेगा ऑप्शन बी 3t/2। फिर आता है कि the two ends of a metal rod are maintained at temperature of 4 degrees Celsius and 4 degrees Celsius. The rate of the heat flow in the rod is found to be charge joule per second. If the ends are maintained at a temperature of 200 degrees Celsius to 4 degrees Celsius, the rate of the heat flow कितना हो जाएगा, तो dq/dt चार्ज जूल पर सेकंड दिया हुआ, डेल्टा टी दिया हुआ 2 माइनस 2 4 इक्वल 10 डिग्री सेल्सियस, डेल्टा टी 1 1 माइनस 4 इक्वल टू 10 डिग्री सेल्सियस, तो dq/t कितना हो जाएगा, the rate of the heat flow is directly proportional to the temperature difference when the temperature difference in both the cases is same, that means 10 degrees Celsius. So the same rate of the heat flow will be in the second case, so dq/dt कितना हो जाएगा 4 जूल पर सेकंड, तो इसका आंसर कितना जाएगा, इसका आंसर ऑप्शन डी 4 जूल पर सेकंड। नेक्स्ट है if certain quantity of the butter cools from the 40 degrees Celsius to 5 degrees Celsius in the next 5 minutes and the 1 degrees Celsius in the next 5 minutes, the temperature of the surrounding कितना हो जाएगा, तो 70 minus 60 by 5 equal to k 55c minus t, और 10 by 5 equal to k 55c minus t, तो for the second case 55 minus 54 by 5 is equal to k 57 minus t, जहाँ 57 डिग्री सेल्सियस is the average of the 50 डिग्री सेल्सियस and 54 डिग्री सेल्सियस, तो 10 by 6 is equal to 55 minus t by 57 minus t, तो t equal to कितना आएगा 45 डिग्री सेल्सियस, पड़ेगा ऑप्शन ए 45 डिग्री सेल्सियस। नेक्स्ट है कि piece of the iron is heated in a flame, if the first becomes dull red, then becomes reddish yellow and finally turn to the white hot. The correct explanation for the above observation is possible by using, तो ऐसा हो जाएगा Bn's displacement लॉ से, तो इक्वेशन फॉर द Bn's displacement लाई गिवन बाय लैम्डा t is equal to होता है कांस्टेंट। फिर आता है if the radius of a star is r and it acts as a black body, what would be the temperature of the star in which the rate of the energy production is q, तो for the Stephen's law E is equal to the sigma t के पावर 4, for the rate of the energy production q is equal to हो जाएगा a into a, यानी q is equal to हो जाएगा sigma t के पावर 4 गुना 4 पाई r स्क्वायर, तो टेम्परेचर ऑफ द स्टार हो जाएगा T इक्वल टू क्यू बाई 4πr² इंटू सिग्मा के पावर 1/4। तो आंसर उसको क्या जाएगा, आंसर जाएगा ऑप्शन डी कि क्यू बाई 4πr² इंटू सिग्मा के पावर 1/4। फिर आता है कि cylindrical metallic rod in the thermal contact with the two reservoir of the heat at its two ends conducts an amount of the heat q in the time t. The metallic rod is melted and the material is formed into a rod of the half the radius of the original rod. So what is the amount of the heat conducted by the new rod when placed in the thermal contact with the two reservoir in the time t? So in the steady state of the amount of the heat flowing from the one phase to another phase in the time t given by q is equal to k theta 1 minus theta 2 into t by L, where k is the coefficient of the thermal conductivity of the material of the rod. तो Q by T directly proportional to A by L यानी R square by L. तो as the metallic rod is melted and the material is formed into a rod of the half radius, तो V1 is equal to V2 यानी पाई 1 R1 के स्क्वायर L1 इक्वल टू पाई R2 के स्क्वायर L2। तो L1 इक्वल टू कितना हो जाएगा L2 बाई 4। तो Q1 बाई Q2 कितना हो जाएगा, Q2 इक्वल टू हो जाएगा Q1 बाई 16 यानी आंसर पड़ेगा कितना, ऑप्शन बी Q बाई 16। नेक्स्ट है कि ब्लैक बॉडी एट 245 डिग्री सेल्सियस रेडिएट हीट एट a temperature of 5 Kelvin per coulomb per second at a temperature of 445 degree Celsius. The rate of the heat radiated in the same minute कितना हो जाएगा। तो अकॉर्डिंग टू द स्टीफन लॉ E इज इक्वल टू सिग्मा टी के पावर 4, जहाँ सिग्मा क्या है, स्टीफन कांस्टेंट है। तो टी टेम्परेचर है तो E1 बाई E2 हो जाएगा T1 बाई T2 के होल 4। तो E2 इक्वल टू हो जाएगा 7 गुना 273 प्लस 727 बाई 273 प्लस 227 का पावर 4। तो यहाँ पे कितना आ रहा है 112 कैलोरी पर सेंटीमीटर स्क्वायर पर 112 कैलोरी सेंटीमीटर स्क्वायर पर सेकंड। तो इसका आंसर कितना आ जाएगा, इसका आंसर आएगा ऑप्शन सी 112। नेक्स्ट है कि the two ends of a rod of length L and uniform cross section area A are kept at the two temperature T1 and T2, जहाँ T1 greater than T2 है। The rate of the heat transfer TQ by dt through the rod in a steady state कितना हो जाएगा। तो for a rod of the length L and area of the cross section A whose faces are maintained at a temperature T1 and T2 respectively, then N is the steady state, the rate of the heat flow from the one phase to another phase in the time t। तो dq by dt हो जाएगा k T1 minus T2 by L। तो इसका आंसर कितना जाएगा, ऑप्शन है dq by dt equal to k T1 minus T2 by L। फिर आता है कि ब्लैक बॉडी इज एट 45 डिग्री सेल्सियस, इट emits energy at a rate which is proportional to the, according to the Stephen's law E is directly proportional to T के power 4 और E is equal to sigma T के power 4, where sigma is the constant of the proportionality and called the Stephen constant. Its value is 5.64 minus 8 watt per meter square per Kelvin के पावर 4। तो E डायरेक्टली प्रोपोर्शनल टू 27 प्लस 273 के पावर 4। तो E जो हो जाएगा डायरेक्टली प्रोपोर्शनल टू 1000 के पावर 4। तो आंसर आएगा ऑप्शन बी 1000 के पावर 4। फिर आता है assuming the sun to have a spherical outer surface of radius r radiating like a black body at a temperature T degree Celsius, the power received by the unit surface normal to the infinite ray at a distance r from the center of the sun where sigma is the Stephen constant। तो कितना हो जाएगा 35 का जाएगा कितना, from the Stephen's law the rate at which the energy radiated by the sun at its surface P is equal to sigma 4 by r square T के पावर 4। तो I is equal to 1 P by 4 by r square यानी कि कितना जाएगा सिग्मा r square T के पावर 4 by r square यानी सिग्मा r square T प्लस 273 के 4 by r square। तो आंसर पड़ेगा ऑप्शन डी कि सिग्मा r square T प्लस 273 के पावर 4 by r square। आंसर पड़ेगा ऑप्शन डी। फिर आता है ब्लैक बॉडी एट 1245 डिग्री इमिट्स रेडिएशन विथ मैक्सिमम इंटेंसिटी एट ए वेवलेंथ ऑफ 5 एंगस्ट्रॉम। इफ द टेम्परेचर ऑफ द बॉडी इंक्रीज बाय द 1000 डिग्री सेल्सियस, द मैक्सिमम इंटेंसिटी कितना हो जाएगा। तो लैम्डा इंटू टी होता है कांस्टेंट। तो लैम्डा बाई लैम्डा, लैम्डा डेफ बाई लैम्डा इक्वल टू टी बाई टी डेफ। तो यहाँ फिर लैम्डा डेफ निकालेंगे तो कितना आ रहा है 3000 एंगस्ट्रॉम। तो आंसर पड़ेगा ऑप्शन डी 3000 एंगस्ट्रॉम। नेक्स्ट है which of the following circular rods given radius r and the length L is made of the same material and which ends are maintained at the same temperature will conduct the most heat। तो as from the law of the heat transport through the conduction, the H is equal to the delta Q by delta T यानी K T1 minus T2 by L। तो H directly proportional to R square by L हो जाता है, where R is equal to 2 R naught, L is equal to 2 L naught। तो H directly proportional to R 2 R naught by K square by 2 L naught। तो H directly proportional to 2 R naught K square by L naught। when r is equal to 2 r naught, L is equal to L naught, तो h directly proportional to 2 r naught का square by L naught यानी h directly proportional to 4 r naught का square by L naught। तो when r is equal to r naught, L is equal to L naught, तो h directly proportional to r naught का square by L naught। तो when r is equal to r naught, L is equal to 2 L naught, h directly proportional to r naught का square by 2 L naught। It is obvious that heat condition will be more in the case of the B। तो इसका आंसर क्या आ जाएगा, इसका आंसर आएगा ऑप्शन बी r इक्वल टू 2 L naught, आर इक्वल टू 2 आर नॉट और एल इक्वल टू एल नॉट। आंसर पड़ेगा 35 का बी, 35 का बी। नेक्स्ट आता है कि लैम्डा एम द नॉट सॉलिड वेवलेंथ एट विच द रेडिएटिव इमिशन फ्रॉम ए ब्लैक बॉडी एट ए टेम्परेचर टी केल्विन मैक्सिमम एट। तो लैम्डा एम इंटू टी इक्वल टू कांस्टेंट। तो लैम्डा जो होगा इनवर्सली प्रोपोर्शनल टू टी, तो लैम्डा जो होगा टी के पावर -1। तो आंसर पड़ेगा ऑप्शन डी लैम्डा डायरेक्टली प्रोपोर्शनल टू के बराबर -1। फिर आता है कि वी कंसीडर द रेडिएशन इमिटेड बाय द ह्यूमन बॉडी व्हिच ऑफ द फॉलोइंग स्टेटमेंट इज ट्रू। तो द हीट रेडिएशन इमिटेड बाय द ह्यूमन बॉडी इज in the infrared radiation, their wavelength is of the order of 1.9 × 10⁻⁵ मीटर, 10⁻³ मीटर, which of course the range of the infrared region। तो इसका आंसर कितना जाएगा? ऑप्शन सी, द रेडिएशन इमिटेड एज इन द इंफ्रारेड रीजन। फिर आता है कंसीडर ए कंपाउंड स्लैब consisting of two different materials having the equal thickness and the thermal conductivity K and 2 K respectively। The equivalent thermal conductivity of the slab कितना हो जाएगा? तो Q इक्वल टू K डेल्टा थीटा बाई एल, जहाँ K है जो थर्मल कंडक्टिविटी है, डेल्टा Q चेंज इन टेम्परेचर, A है एरिया ऑफ द स्लैब, L है थिकनेस। तो K1 A डेल्टा T1 बाई एल, K2 A डेल्टा T2 बाई एल इज इक्वल टू K डेफ डेल्टा T1 प्लस डेफ बाई 2L। अब अगर यहाँ से निकालेंगे इसको सोल्व करके, डेल्टा K डेल्टा T1 इक्वल टू K2 डेल्टा T2 यानी K डेफ बाई 2 इज इक्वल टू डेल्टा T1 प्लस डेल्टा T2 बाई C। तो डेल्टा T1 इक्वल टू C बाई K1, डेल्टा T2 इक्वल टू C बाई K2। तो यहाँ से निकालेंगे K डेफ तो हो जाएगा कितना? 4/3K। तो आंसर आएगा इसका 4/3K, ऑप्शन बी। नेक्स्ट है कि फॉर ब्लैक बॉडी एट द टेम्परेचर 45 डिग्री सेल्सियस इट्स रेटिंग पावर इज 7 वाट एंड टेम्परेचर ऑफ द सराउंडिंग इज 45 डिग्री सेल्सियस। इफ द टेम्परेचर ऑफ द ब्लैक बॉडी चेंज टू 45 डिग्री सेल्सियस देन दिस रेटिंग पावर कितना हो जाएगा? तो बोल्टमैन करेक्टेड स्टीफन लॉ एंड सब्स्टिट्यूटेड दैट अमाउंट ऑफ द रेडिएशन इमिटेड बाय द बॉडी not only depends upon the temperature of the body but also depends on the temperature of the surrounding. The rated power of the body is P is equal to sigma T to the power 4 minus T naught to the power 4, where T naught is the absolute temperature of the surrounding and T is the temperature of the body. So for two different cases of the disk of radiation power, you know P2 by P1 is T2 to the power 4 minus T naught to the power 4 by T1 to the power 4 minus T naught to the power 4। तो P1 हो जाएगा 60 वाट, यानी T1 हो जाएगा 45 डिग्री 1000 केल्विन, T नॉट हो जाएगा 245 डिग्री सेल्सियस यानी 500 केल्विन, T2 हो जाएगा 1500 केल्विन। तो P2 कितना आ जाएगा? 320 वाट। तो इसका आंसर कितना जाएगा? इसका आंसर आएगा ऑप्शन डी, 320 वाट। फिर आता है कि consider the two rods of the same length having different specific heat F1 and F2, thermal conductivity K1 and K2, and area of the cross section A1 and A2, and both having a temperature T1 and T2 at their ends. If the rate of the loss of the heat due to the conduction are equal, then तो rate of the loss of heat by the conduction H is equal to the delta Q by delta T यानी K T1 minus T2 by L। For the first rod H1 is equal to the K1 A1 T1 minus T2 by L1। For the second rod H2 is equal to होता है K2 A2 T1 minus T2 by L2। तो लेकिन L1 is equal to L2 है, तो H1 is equal to हो जाएगा H2। That means the same rate of the heat loss of the heat through the conductor। So we have K1 A1 T1 minus T2 equal to K2 A2 T1 minus T2। तो K1 A1 is equal to हो जाएगा K2 A2। तो इसका आंसर कितना जाएगा? ऑप्शन है K1 A1 is equal to हो जाएगा K2 A2। फिर आता है कि BH displacement law expresses relation between the, तो आंसर आएगा ऑप्शन ए, wavelength corresponding to the maximum energy and absolute temperature। तो according to the BH displacement law, the quantity of the energy radiated out by a body is not uniformly distributed over all the wavelength emitted by it. It is maximum for a particular wavelength lambda which is different at a different temperature. As the temperature is increased, the value of the wavelength which carry the maximum energy decreased. The statement of this law is the wavelength corresponding to the maximum energy is inversely proportional to the absolute temperature। तो lambda inversely proportional to temperature, तो lambda into m into t equal to क्या आ जाएगा? कांस्टेंट। फिर नेक्स्ट क्वेश्चन है कि which of the following is close to the an ideal black body। तो आंसर आएगा ऑप्शन बी, cavity maintained at the constant temperature। नेक्स्ट है कि rate of the heat flow through a cylinder H, cylinder rod is H1, the temperature of the ends of the rod are T1 and T2। If all the dimensions of the rod become double and temperature become difference remains same and the rate of the heat flow becomes H2, then the H2 by H1 हो जाएगा L2 by L1 and H2 L1 by L1। तो L thickness of the H directly proportional to A by L हो जाएगा। तो यहाँ से अगर निकाल लें तो डायरेक्टली प्रोपोर्शनल टू एल, तो H2 by H1 हो जाएगा L2 by L1 यानी 2L1 by L1। तो H2 इक्वल टू हो जाएगा 2H1। तो इसका आंसर कितना जाएगा? ऑप्शन है H2 इक्वल टू हो जाएगा 2H1। फिर आता है द वेवलेंथ corresponding to the maximum intensity of the radiation emitted by a source at temperature 2000 Kelvin lambda, then what is the wavelength corresponding to the maximum intensity of radiation at a temperature of 3000 Kelvin। तो बी एच डिस्प्लेसमेंट लैम्डा इंटू टी इक्वल टू कॉन्स्टेंट, तो यहाँ पे लैम्डा 1 T1 इक्वल टू लैम्डा 2 T2, तो लैम्डा 2 इक्वल टू लैम्डा T1 बाई T2। तो लैम्डा 2 इक्वल टू आएगा 2/3 लैम्डा, यानी कि इसका आंसर आएगा ऑप्शन ए 2/3 लैम्डा। फिर रहता है बीच ऑफ द फॉलोइंग प्रोसेस डिपेंड्स ऑन द ग्रेविटी। तो ऑप्शन बी कन्वेक्शन है जो ग्रेविटी पर डिपेंड करता है। अगला सवाल है कि द रेडिएंट एनर्जी फ्रॉम द सन इन्सिडेंट नॉर्मली एट द सरफेस ऑफ द अर्थ इज 20 कैलोरी पर मीटर स्क्वायर per minute। तो what would be the radiant energy incident normally on the earth if the sun had a temperature twice of the present one। तो स्टीफन ला के अनुसार ई डायरेक्टली प्रोपोर्शनल टू सिग्मा के पावर T4 और ई डायरेक्टली प्रोपोर्शनल टू T के पावर 4, तो E1/E2 T1/T2 के पावर 4। यहाँ से अगर निकालेंगे तो E2 आ जाएगा कितना, 320 किलो कैलोरी पर मीटर स्क्वायर पर मिनट। तो आंसर ऑप्शन सी 320 किलो कैलोरी पर मीटर स्क्वायर पर मिनट। फिर ब्लैक बॉडी इज एट टेम्परेचर ऑफ 500 Kelvin, it emits energy at rate Bg proportional to, according to Stephen's law, energy emitted E directly proportional to T power 4, तो E equal to sigma T के पावर 4। तो E directly proportional to 500 के पावर 4, तो अगर यहाँ से निकाल लें तो आंसर आएगा ऑप्शन है 500 के पावर 4। फिर आता है कि a beaker full of the hot water is kept in the room if it cools from 80 degrees Celsius to 75 degrees Celsius 51 and from 75 degrees Celsius to 40 degrees Celsius 52 minutes and from 40 degrees Celsius to 50 degrees Celsius 83 minutes, देन तो आंसर आएगा ऑप्शन सी कि सबसे बड़ा हो जाएगा T3, फिर T2, सबसे कम होगा T1, तो यहाँ से निकल जाएगा ये। नेक्स्ट है कि बॉडी कूल्स फ्रॉम 50 डिग्री सेल्सियस टू 49.9 डिग्री सेल्सियस इन द 5 सेकंड, हाउ लॉन्ग विल टेक टू कूल फ्रॉम 40 डिग्री सेल्सियस टू 49.9 डिग्री सेल्सियस एंड 30 डिग्री सेल्सियस, न्यूटन्स ऑफ कूलिंग टू वैलिड। तो dt/dt होता है T माइनस TF, यानी dt/dt होता है KT T माइनस TF। तो यहाँ से अगर निकालेंगे तो ये कितना होगा 10 सेकंड, तो ऑप्शन बी 10 सेकंड। If the temperature of the sun is double, the rate of the energy received on earth will be factor of, तो आंसर आएगा 15। ये डायरेक्टली प्रोपोर्शनल टू T के पावर 4 होता है, तो ये हो जाएगा सिग्मा T के पावर 4, तो आ जाएगा कितना 15 टाइम्स। ये है थर्मल प्रॉपर्टीज ऑफ मैटर का NCERT। तो इसमें देख रहे हैं कि we have all common sense notion of the heat and the temperature. Temperature is a measure of the hotness of a body. A kettle with boiling water is hotter than a box containing ice. In physics, we need to define the notion of the heat, temperature, etc. more carefully. In this chapter, we will learn about what heat is and how it is measured, and study the various processes by which heat flow from the one body to another. Along the way, you will study find blacksmith hit the iron ring before pinning an iron rim on the wooden wheel of a horse cart, and why the wind at the beach often reverses direction after the sun goes down. You will also learn what happens when water boils for fish and its temperature does not change during this process, even though a great deal of the heat is flowing into or out of it. So temperature and the heat. We can begin studying the thermal property of the matter with a definition of the temperature and the heat. Temperature is a relative measure or the indication of the hotness or the coldness. A hot utensile is said to have a high temperature and ice cubes to have a low temperature. An object that has a higher temperature than the other object is said to be hotter. Note that hot and cold are relative terms like tall and short. We can perceive temperature by touch, however, this temperature sense is somewhat unreliable and its range is too limited to be useful for the scientific purpose. We know from the experience that a glass of the ice cold water left on a table on a hot summer day eventually warms up, whereas a cup of the hot tea on the same table cools down. It means that when the temperature of the body, ice cold water or a hot tea in this case, and its surrounding medium are different, heat transfer takes place between the system and the surrounding medium until the body and the surrounding medium are at the same temperature. We also know that in the case of the glass tumbler of the ice cold water, heat flows from the environment to the glass tumbler, whereas in the case of the hot tea, it flows from the cup of the hot tea to the environment. So we can say that heat is a form of the energy transferred between the two more system or the system and its surrounding by virtue of the temperature difference. The SI unit of the heat energy transferred is expressed in the joule, while SI unit of the temperature in the Kelvin and degree Celsius is commonly used unit of the temperature. When an object is heated, many changes may take place. Its temperature may rise, it may expand or change the state. We will study the effect of the heat on the different body in the later section. फिर आता है मेजरमेंट ऑफ टेम्परेचर। तो मेजरमेंट ऑफ टेम्परेचर यू ऑब्टेन यूजिंग ए थर्मोमीटर। मैनी फिजिकल प्रॉपर्टीज ऑफ द मटेरियल्स चेंज इफ sufficiently with temperature. Some such property are used as the basis for the constructing thermometers. The commonly used property is the variations of the volume of the liquid with the temperature. For example, in the common liquid in the gas thermometer, mercury, alcohol, etc. are used whose volume varies linearly with the temperature over a wide range. Thermometers are calibrated so that a numerical value may be assigned to a given temperature in the property scale. For the definition of any standard scale, two fixed reference points are needed. Since all substances change dimensions with temperature, an absolute reference for the expansion is not available. However, the necessary fixed points may be correlated to the physical phenomena that always occur at the same temperature. The ice point and the steam point of the water are two convenient fixed points and are known as the freezing point and the boiling point respectively. These 2 points are the temperature at which the pure water freezes and the boils under the standard pressure. The two familiar temperature scales are the Fahrenheit temperature and scale and the Celsius temperature scale. The ice and the steam water have the values 32 degrees Fahrenheit and 4 degrees Fahrenheit respectively on the Fahrenheit scale, and 0 degrees Celsius and 4 degrees Celsius on the Celsius scale. On the Fahrenheit scale, there are 120 equal intervals between the two reference points, and on the Celsius scale, there are 4. अब यहाँ पर दिखा है plot of the Fahrenheit temperature versus the Celsius temperature Tc. A relationship for converting between the two scales may be obtained from a graph of the Fahrenheit temperature versus the Celsius temperature on a straight line, which equation is T minus 32/4 equal to T C by 4. फिर आता है ideal gas equation and the absolute temperature. The liquid in the gas thermometer for different readings for the temperature other than the fixed point because of the different expansion property. A thermometer that uses gas, however, gives the same reading regardless of which gas we used. Experiments show that all the gases at low density exhibit the same expansion behavior. देखो यहाँ से कितना अच्छा है जो स्टेटमेंट रीजन है जो बन सकता है. The variables that describe the behavior of a given quantity: mass of a gas or pressure, volume and the temperature. PVT, where T is equal to small t plus 273.15, T is the temperature in the degrees Celsius. When temperature is held constant, the pressure and the volume of a quantity of a gas are related as P is equal to constant. This relationship is known as the Boyle's law. When the pressure is held constant, the volume of a quantity of the gas is related to the volume V by T is equal to constant. This relationship is known as Charles law. उसके बाद कहता है कि low density gas obey this law which may be combined into a single relationship. Notice that the PV is equal to constant and V by T constant for a given quantity of the gas. When P by T should also be constant, this relationship is known as the ideal gas law. It can be written in a more general form that applies not just to given a quantity of a single gas but to any quantity of any low density gas, and is known as the ideal gas equation. So PV is equal to mu R or PV is equal to mu RT, where mu is the number of the moles of the sample of the gas and R is the universal gas constant. तो R equal to 8.3 जूल पर मोल पर केल्विन. अब यहाँ पर दिया हुआ है प्रेशर वर्सेस टेम्परेचर ऑफ ए लो डेंसिटी गैस एट ए कांस्टेंट टेम्परेचर पर. तो ये दिया हुआ है प्रेशर और ये दिया हुआ है टेम्परेचर. नेक्स्ट आता है कि इन द इक्वेशन 10.2 वी हैव लर्न दैट द प्रेशर एंड द वॉल्यूम आर डायरेक्टली प्रोपोर्शनल टू द टेम्परेचर. PV जो होता है डायरेक्टली प्रोपोर्शनल टू द टेम्परेचर. दिस रिलेशनशिप अलाउ गैस टू बी यूज्ड टू मेजर द टेम्परेचर इन a constant volume gas thermometer. Holding the volume of a gas constant, it gives P directly proportional to T. Thus, with a constant volume gas thermometer, temperature read in the terms of the pressure. A plot of the pressure versus temperature gives a straight line in the case 5 in figure 10.2. However, measurements on the real gas deviate from the values predicted by the ideal gas law at low temperature, but the relationship is linear over a large temperature range, and it looks as though the pressure might reach zero with decreasing temperature. If the gas continues to be gas, the absolute minimum temperature for an ideal gas therefore inferred by the extrapolating the straight line to the axis as shown in figure 10.3. This temperature is found to be minus 273.15 degrees Celsius and is designated at absolute zero. Absolute zero is the foundation of the Kelvin temperature scale or absolute scale temperature. यहाँ पर दिया plot of the preferred buffer temperature and extrapolation of the line for low density gases indicates the same absolute zero temperature. ये दिया prefer, इधर दिया temperature का graph. Named after the on this scale minus 273.15 degrees Celsius taken at the 0 point, that is the 0 Kelvin. फिर आता है comparison on the Kelvin, Celsius and the Fahrenheit temperature scale. The size of the unit in the Kelvin and the Celsius temperature scale is the same. For temperature on these scales are related by T equal to Tc plus 273.15. फिर आता है thermal expansion. So you may have observed that sometimes filled bottles with metallic lids are so tightly screwed that one has to put the lid in the hot water for some time to open it. This would allow the metallic lid to expand, thereby leading it to the unscrew easily. In the case of the liquid, you may have observed that mercury in the thermometer rises when the thermometer is put in the slightly warm water. If we take out the thermometer from the warm water, the level of the mercury falls again. Similarly, in the case of the gases, a balloon partially inflated in a room may expand to the full size when placed in the warm water. On the other hand, a fully inflated balloon, when immersed in the cold water, would start shrinking due to the contractions of the air inside. It is a common experience that most substances expand on the heating and contract on the cooling. A change in the temperature of a body causes change in its dimension. The increase in the dimension of a body due to the increase in its temperature is called the thermal expansion. The expansion of the length is called the linear expansion. The expansion in the area is called the area expansion, and the expansion in the volume is called the volume expansion. फिर यहाँ पर दिखाया हुआ है ये हो गया linear expansion. Delta L by L is equal to alpha delta T. Aerial expansion delta A by A is equal to 2 alpha delta T और delta B by B is equal to 3 alpha delta T हो गया volume expansion. So if the substance is in the form of a long rod, then for the small change in delta T, the fractional change in the delta L by L is directly proportional to delta T. डेल्टा एल बाई एल होता है अल्फा डेल्टा टी। फिर आता है कि बेर अल्फा इधर नोन एज द कोफिशिएंट ऑफ द लीनियर एक्सपेंशन और लीनियर एक्सपेंसिविटी एंड इज कैरेक्टरिस्टिक ऑफ द मटेरियल ऑफ द रॉड। In the table 10.1, typical average values of the coefficient of the linear expansion for some material in the temperature range from 0 to 4 degrees Celsius are given. From that table, compare the value of the alpha for the glass and the copper. We find that copper expands about 5 times more than the glass for the same rise in the temperature. Normally, metal expands more and have relative high value of the alpha T. फिर यहाँ पर दिखा हुआ values of the coefficient of the linear expansion for some material. So similarly, we consider the fractional change in the volume delta V by V of a substance for the temperature change delta T and define the coefficient of the volume expansion for the volume expansion alpha V. तो अल्फा भी इक्वल टू आता है डेल्टा भी बाई भी 1 by delta T. Here alpha B is also a characteristic of the substance but is not strictly a constant. It depends on the in general on the temperature. It is seen that alpha V becomes constant only at a high temperature. तो यहाँ पर दिया हुआ अल्फा भी और कोफिशिएंट यहाँ पर दिया हुआ टेम्परेचर का ग्राफ, ये हो गया कोफिशिएंट ऑफ द वॉल्यूम एक्सपेंशन ऑफ द कॉपर एज ए फंक्शन ऑफ द टेम्परेचर। फिर आता है कि टेबल 10.2 गिव्स द वैल्यू ऑफ द कोफिशिएंट ऑफ द वॉल्यूम एक्सपेंशन ऑफ सम common substances in the temperature range of 0 to 4 degrees Celsius. You can see that thermal expansion of the substances solid and liquid is rather small, with that material like the pyrex glass and invar a special role iron nickel alloy having particularly low value of the alpha B. From this table we find that the value of the alpha B for the alcohol ethanol is more than the mercury and expands more than the mercury for the same rise in the temperature. यहाँ पर the value of the coefficient of the volume expansion for the some substances. फिर आता है वाटर की an anomalous behavior. It contracts on the heating between 0 degree and the 4 degree Celsius. The volume of a given amount of the water decreases as it equals from the room temperature until the temperature reaches 4 degrees Celsius. Below 4 degrees Celsius, the volume increases and therefore the density decreases. This means that the water has the maximum density at 4 degrees Celsius. This property has the important environmental effect. Body of the water, such as the lakes and the ponds, freeze at the top first. At a lake called towards 4 degrees Celsius, water near the surface loses energy to the atmosphere, becomes denser and sinks. The warmer, the less denser water near the bottom rise. However, once the cold water on the top reaches temperature below 4 degrees Celsius, it becomes less dense and remains at the surface where it freezes. If water did not have this property, lakes and the ponds would freeze from the bottom up, which would destroy much of the animal and the plant life. फिर आता है कि gas phase at the ordinary temperature expands more than the solids and the liquid. For liquids, the coefficient of the volume expansion is relatively independent of the temperature. However, for the gas phase, it is independent on the temperature. For an ideal gas, the coefficient of the volume expansion at the constant pressure can be found from the ideal gas equation. P v is equal to mu RT. At constant pressure, P v delta V is equal to mu R delta T. So delta V by delta V by V is equal to delta T by T. Alpha V is equal to 1 by delta T for ideal gas. At 0 degrees Celsius, alpha V is equal to 3.7 10 to the minus 3 per Kelvin, which is more larger than that of the solid and the liquid. Equation 10.64 that the temperature dependence of alpha V it decreases with increasing temperature. For a gas at the room temperature and the constant pressure, alpha V is about 37 to the 4 minus 6 per Kelvin as much as the order of the magnitude is larger than the coefficient of the volume expansion of a typical liquid. There is a simple relation between the coefficient of the volume expansion alpha B and the coefficient of the linear expansion alpha. Imagine a cube of the length L that expands equally in all directions when its temperature increased by the delta T. We have delta L is equal to alpha L delta T. So delta V is equal to L plus delta L cube minus L cube is equal to 3 L square delta L. In the equation 10.7, the terms the delta L square and the delta L cube have been neglected since delta is small compared to the I. So delta V is equal to 3V delta L by L and 3V alpha delta T, which gives alpha V is equal to 3 alpha. What happens by preventing the thermal expansion of a rod by fixing its ends rigidly? Clearly, the rod acquires a compressive strain due to the external force provided by the rigid support at the strain at the ends. The corresponding stress set up in the rod is called the thermal stress. For example, consider a steel rail of the length 5 meter and area of the cross section 40 cm square that is prevented from expanding while the temperature rises by the 10 degrees Celsius. The coefficient of the linear expansion of a steel is alpha of steel equal to 1.2 another for minus March Kelvin. Thus, the compressive strain is delta L by L and delta T 1.2 another for minus 5 another 10 and 1.2 another for minus 4. Young model of steel gamma of steel equal to another for power 11 Newton meter square. Therefore, the thermal stress developed is delta F by is equal to gamma of steel delta L by L and 2.4 another for power 5 Newton meter square, which correspond to an external force of delta F equal to a gamma of steel delta L by L यानी 2.4 गुना 10 पावर 7 ना 40 गुना 10 पावर माइनस 4 यानी कि 10 पावर 5 न्यूटन. If two such steel rails fixed at the outer ends are in contact at the inner ends, a force of this magnitude can easily bend the rail. फिर यहाँ पर इसको क्वेश्चन है कि फॉर दैट द कोएफिशिएंट ऑफ द एरियल एक्सपेंशन डेल्टा ए बाई ए इंटू डेल्टा टी ऑफ ए रेक्टेंगुलर शीट ऑफ द सॉलिड ट्वाइस इट्स लिनियर एक्सपेंसिविटी अल्फा टी। तो यहाँ पर दिया हुआ ए डेल्टा बी, ए3 दिया हुआ है डेल्टा बी और डेल्टा टू दिया हुआ है बी डेल्टा ए। तो consider a rectangular sheet of the solid material of the length a and the breadth b. When the temperature increased by the delta t, a increase in by the delta is equal to alpha delta t and b by the delta b is equal to alpha b delta t. From the given 10.8, the increase in area delta is equal to delta f1 plus delta to the below delta f3. Delta is equal to a delta b delta a और डेल्टा इंटू डेल्टा बी। तो यहाँ पे करेंगे तो सिंस अल्फा 1 इक्वल टू 10⁻5 केल्विन फ्रॉम द टेबल 10.1, the product alpha delta t for the fractional temperature is small in compared to the 2 and may be negative, hence delta by a is equal to 1 by delta t यानी 2 अल्फा हो जाता है। फिर आता है कि black smith fixes iron ring on the rim of the wooden bill of a horse cart, the diameter of the rim and the iron ring for 5.243 and the 5.231 meter respectively at 45 degrees Celsius. तो बाहर temperature should the ring be heated for to fit the rim of the bill. तो T1 is equal to 45 degrees Celsius, LT1 is equal to 5.231 meter और LT12 is equal to 5.243 meter. तो L12 is equal to LT1 1 plus alpha T2 minus T1. So 5.243 is equal to 5.231 plus 1.20 10.5 पर केल्विन यानी T2 minus 45 डिग्री सेल्सियस। तो T2 इक्वल टू कितना हो जाएगा 218 डिग्री सेल्सियस। फिर आता है स्पेसिफिक हीट कैपेसिटी। तो कहता है टेक सम वाटर इन अ vessel and start heating it on a burner. Soon you will notice that bubbles will begin to move upward as the temperature reaches to the motion of water particles increases till it becomes turbulent as the water starts boiling. What are the factors on which the quantity of the heat required to raise the temperature of a substance depend? In order to answer this question, in the first step, heat a given quantity of the water to raise the temperature by 20 degrees Celsius and note the time taken. Again, take the time, same amount of the water and raise the temperature by the 20 degrees Celsius using the same source of the heat. Note the time taken by using a stopwatch. You will find it that about twice the time and therefore double the quantity of the heat required to raising the twice the temperature of the same amount of the water. Rather, in the second step, now suppose you take double the amount of the water and heat it using the same heating arrangement to raise the temperature by 20 degrees Celsius. You will find the time taken is again twice that required in the first step. In the third step, in the place of the water, now heat the same quantity of the some oil, some mustard oil, and raise the temperature again by the 20 degrees Celsius. Now, note that the time by the same stopwatch, you will find that the time taken by the shorter, and therefore the quantity of the heat required would be less than that required by the same amount of the butter for the same rise in the temperature. Therefore, observations show that the quantity of the heat required to warm a given substance depend upon mass m, the change in the temperature delta t, and the nature of the substance. The change in the temperature of a substance when a given quantity of heat is absorbed or rejected by it is characterized by a quantity called the heat capacity of that substance. We define heat capacity F of a substance as F equal to delta Q by delta T, where delta Q is the amount of the heat supplied to the substance to change its temperature from T to delta T. You have observed that if equal amount of the heat is added to the equal mass of the different substances, the resulting temperature changes will not be same. It implies that every substance has a unique value of the amount of the heat absorbed or given off to the change the temperature of the unit mass of by 1 unit. This quantity is referred to the specific heat capacity of the substance. If delta Q stands for the amount of the heat absorbed or given off a substance for of mass m when it undergoes a temperature change delta T, then the specific heat capacity of the substance given by F equal to capital F by m, yani 1 by m delta Q by delta T. The specific heat capacity is the property of the substance which determines the change in the temperature of the substance undergoing no phase change when a given quantity of the heat is absorbed or given off by it. It is defined as the amount of the heat per unit mass absorbed or given off by the substance to change its temperature by 1 unit. It depends on the nature of the substance and its temperature. The SI unit of the specific heat capacity is joule per kg per Kelvin. If the amount of the substance is specified into terms of the mu instead of the mass m in the kg, we can define the heat capacity per mole of the substance C is equal to F by mu and 1 by mu delta Q by delta T, where C known as the molar heat capacity of the substance. Like Fc also depends on the nature of the substance and its temperature. The SI unit of the molar heat capacity is the joule per mole per Kelvin. However, in correction with the specific heat capacity of the gas phase, additional condition may be needed to define C. In this case, heat transfer may can be achieved by keeping either pressure or volume constant. If the gas is held under the constant pressure during the heat transfer, then it is called as the molar specific heat capacity at the constant pressure and denoted by the Cp. On the other hand, if the volume of the gas is maintained during the heat transfer, then the corresponding molar specific heat capacity is called the molar specific heat capacity at the constant volume and noted by the Cb. For details, see the chart. Chapter 11. Table 13.3 Lift measure of specific heat capacity of the sum of times at the atmospheric pressure and ordinary temperature. But the table 10.4 lift from molar specific heat capacity of the sum of gases. Table 10.3 you can note that water had the highest specific heat capacity compared to the other substances. For this reason, water is also used as a coolant in the automobile radiator as well as in the heater in the hot water bags. Owing to this high specific capacity, water burns up more fuel than the land during the summer and consequently wind from the sea has a cooling effect. Now you can tell why in the desert areas the earth surface burns up quickly during the days and cools quickly at night. अब यहाँ पर कुछ दिया हुआ है specific heat capacity of some substance at room temperature and at atmospheric pressure पर जो दिया हुआ है एल्युमिनियम कॉपर का दिया हुआ है फिर दिया हुआ है कार्बन लीड सिल्वर टंगस्टन और वाटर का तो वाटर का देख रहे हैं सबसे ज़्यादा है 4186 है जूल पर केजी पर केल्विन इसमें वाटर का सबसे ज़्यादा है और अगर इधर देखें तो इधर भी है जो एडिबल ऑयल का है जो सबसे मतलब केरोसिन का है जो सबसे ज़्यादा दिए हुए। नेक्स्ट आता है मोलर स्पेसिफिक हीट कैपेसिटी ऑफ द सम गैसेज यानी कि गैस दिया हुआ है और उसका सीपी दिया हुआ है जूल पर मोल पर केल्विन में इधर सीबी दिया हुआ है जूल पर मोल पर केल्विन में। फिर आता है कैलोरीमेट्री तो सिस्टम इज सेड टू बी आइसोलेटेड इफ नो एक्सचेंज और द ट्रांसफर ऑफ द हीट ऑकर्स बिटवीन द सिस्टम एंड इट्स सराउंडिंग व्हेन डिफरेंट पार्ट्स ऑफ एन आइसोलेटेड सिस्टम आर एट डिफरेंट टेम्परेचर a quantity of the heat transfer from the part at the higher temperature to the part at the lower temperature. The heat lost by the part at the higher temperature is equal to the heat loss gained by the part at a lower temperature. Calorimetry means measurement of the heat when a body at higher temperature is brought in contact with another body at a lower temperature. The heat lost by the hot body is equal to the heat gained by the colder body, provided no heat is allowed to escape to the surrounding. A device in which the heat measurement can be done is called a calorimeter. It consists of a metallic vessel and a stirrer of the same material like the copper or the aluminum. The vessel is kept inside a wooden jacket which contains heat insulating material like the glass wool, etc. The outer jacket acts as a heat shield and reduces the heat loss from the inner vessel. There is an opening in the outer jacket through which a mercury thermometer can be inserted into the calorimeter. The following example provides a method by which the specific heat capacity of a given solid can be determined by using the principle heat gained equal to the heat lost. अब यहाँ पर एक क्वेश्चन है कि a sphere of the 0.041 kg aluminum is placed for the sufficient time in a vessel containing the boiling water so that the sphere is at 0 degrees Celsius, 4 degrees Celsius. It is then immediately transferred to 0.14 kg copper calorimeter containing 0.25 kg water at 20 degrees Celsius. The temperature of the water rises and attains a steady state at 23 degrees Celsius to calculate the specific heat capacity of the aluminum. तो इसमें कहता है कि in following this example we follow the fact that at a steady state heat given by an aluminum sphere will equal to the heat lost absorbed by the water and the calorimeter. The mass of aluminum दिया हुआ है 0.047 kg. Initial temperature of the aluminum sphere 4 degrees Celsius है. Final temperature 23 degrees Celsius है. Change in the temperature हो गया delta T equal to 4 plus minus T equal to 43 degrees Celsius. To calculate the specific heat capacity of aluminum be F aluminum. तो amount of the heat lost by the aluminum sphere हो जाएगा M1FL delta T. Mass of the water हो जाएगा 0.25 kg. Mass of calorimeter है 0.14 kg. Initial temperature of the water and calorimeter हो जाएगा 20 डिग्री सेल्सियस. फाइनल टेम्परेचर ऑफ द मिक्सर हो जाएगा 23 डिग्री सेल्सियस. तो चेंज इन टेम्परेचर हो जाएगा 23 माइनस 20 यानी कि 3 डिग्री सेल्सियस. और स्पेसिफिक कैपेसिटी ऑफ वाटर होता है 4.1 at 3 जूल पर केजी पर केल्विन. और स्पेसिफिक कैपेसिटी ऑफ द कॉपर थर्मोमीटर होता है 0.386 3 जूल पर केजी पर केल्विन. The amount of the heat gained by the water and the calorimeter M2FW delta T plus M3FU delta T2. तो M2FW plus M3FU delta T2 आ जाएगा. तो यहाँ से कितना आ रहा है? इतना आ रहा है. In a steady state heat lost by the aluminum sphere is equal to heat gained by the water plus heat gained by the calorimeter. तो इसको सोल्व करेंगे तो आएगा 0.911 किलो जूल पर केजी पर केल्विन. फिर आता है चेंज ऑफ द स्टेट. To matter mostly normally exist in the three states: solid, liquid, and the gas. A transition from the one of these state to another is called the change of the state. Two common change of the state are solid to the liquid and liquid to the gas, and vice versa. These changes can occur when the exchange of the heat takes place between the systems and the surrounding. To study the change of the state on the heating or cooling, let us perform the following activity. Take some cube of the ice in a beaker. Note that the temperature of the ice start heating it slowly on a constant near the heat surface. Note the temperature after every minute. Continuously stir the mixture of the water and the ice. Draw a graph between the temperature and the time. You will observe no change in the temperature as long as there is no ice in the beaker. In the above process, the temperature of the system does not change even though the heat is continuously supplied. The heat supplied is being utilized in changing the state from solid ice to the liquid water. फिर यहाँ पर जो टेम्परेचर और यहाँ पर टाइम का दिया हुआ है, ए प्लॉट ऑफ द टेम्परेचर वर्सेस टाइम शोइंग द चेंज इन द स्टेट ऑफ द आइस ऑन द हीटिंग. उसके बाद फिर आता है the change of the state from the solid the liquid is called the melting or the fusion, and from the liquid to the solid is called the freezing. It is observed that the temperature remains constant until the entire amount of the solid substance melts. That is, both the solid and the liquid states of the substance coexist in the thermal equilibrium during the change of the states from the solid to the liquid. The temperature at which the solid and the liquid states of the substance with thermal equilibrium with each other is called the melting point. It is characteristic of the substance. It also depends on the pressure. The melting point of the substance for the standard atmospheric pressure is called the normal melting point. Let us do the following activity to understand the process of the melting of the ice. Take a slab of the ice, take a metallic bar and fix two blocks of 5 kg each at its ends. Put the bar over the slab as shown in figure 10.10. We will observe that the bar passes through the ice slab. This happens due to the fact that just below the bar, the ice melts at the lower temperature due to increase in pressure. When the bar has passed, water above the bar freezes again. Thus the bar passes through the slab and the slab does not split. This phenomenon of the refreezing is called the relegation. Skating is possible on the snow due to the formation of the water. Under the skates, water is formed due to the increase of the pressure and it acts as a lubricant. अब यहाँ पर दिखाया हुआ है कि after the whole of the ice gets converted into the water and we had continue after further heating, we shall see that temperature began to rise. The temperature keeps on rising until it reaches nearly 4 degrees Celsius. Minute again becomes steady. The heat supplied is now being utilized to change water liquid state to the vapor or the gaseous state. The change of the state from the liquid to the vapor or gas is called the vaporization. It is observed that the temperature remains constant until the entire amount of liquid is converted into the vapor. That is, both the liquid and the vapor states of the substance coexist in the thermal equilibrium during the change of the state from the liquid to the vapor. The temperature between the liquid and the vapor states of the substance coexist is called the boiling point. Let us do the following activities to understand the process of the boiling point of the water. Take a round bottom flask more than half filled with water, keep it over a burner and fix a thermometer and the steam outlet through the cork of the flask. As water gets fitted in the flask, note that first the air which has dissolved in the water will come out as a small bubbles. Later bubbles of the steam will form at the bottom right as they rise to the cooler water near the top. They condense and disappear. Finally, at the temperature of the entire mass of the water reaches 4 degrees Celsius, bubbles of the steam reach the surface and the boiling is said to occur. The steam in the flask may not be visual, but as it comes out of the flask, it condenses as tiny droplets of the water, giving a foggy appearance. फिर आता है कि if now the steam bottle is closed for a few seconds to increase the pressure in the flask, you will notice that boiling stops. More heat would be required to raise the temperature depending upon the increase in the pressure before boiling begins again. Thus, boiling water increase with increase in the pressure. Now let us remove the burner. Allow water to cool to the 80 degrees Celsius. Remove the thermometer and a steam outlet. Close the flask with the airtight cork. Keep the flask turned upside down on the stand. Pour ice cold water on the flask. Water vapor on the flask condenses, reducing the pressure on the water surface inside the flask. Water begins to boil again. Now at the lower temperature, this boiling point decreases with the decrease in the pressure. This explains why cooking is difficult on the hills. At high altitudes, atmospheric pressure is lower, reducing the boiling point of the water as compared to that of the sea level. On the other hand, boiling point is increased inside the pressure cooker by increasing the pressure. Hence, cooking is faster. The boiling point of the substance at a standard atmospheric pressure is called its normal boiling point. However, all substances do not pass through the three states solid, liquid, gas. There are certain substances which normally pass from the solid to the vapor state directly and vice versa. The change of the solid state to the vapor state without passing through the liquid state is called the sublimation, and the substance is said to be sublime. Dry ice, solid CO2 sublimes and so alpha iodine. During the sublimation process, both the solid and the vapor state of the substance coexist in the thermal equilibrium. फिर यहाँ पर दिखाया हुआ है ट्रिपल पॉइंट ऑफ द वाटर क्या होता है वो दिखाया हुआ है. तो आता है the temperature of a substance remains constant during exchange of the state phase change. A graph between the temperature T and the pressure P of the substance is called a phase diagram of a PT diagram. The following figure shows the phase diagram of the water and CO2. Such a phase diagram of the PT plane into solid region, the vapor region, and the liquid region. The regions are separated by the curves such as the sublimation curve BO, fusion curve AO, and the vaporization curve CO. The points on the sublimation curve represent the state in which the solid and the vapor phase coexist. The point on the sublimation curve BO represent the state in which the solid and the vapor phase coexist. Points of the fusion curve AO represent the states in which the solid and the liquid phase coexist. Points on the vaporization curve CO represent the states in which the liquid and the vapor phase coexist. The temperature and the pressure in which the fusion curve, the vaporization curve, and the solution curve meet, and all three phases of a substance coexist, we call a triple point of the substance. For example, the triple point of the butter is represented by the temperature 243.16 Kelvin and pressure 6.11 - 3 Pascal. तो प्रेफर टेम्परेचर फेज डायग्राम फॉर द वाटर एंड CO2 का है जो दिए हुए। फिर इसके बाद आता है लैटेंट हीट। तो इसमें आता है कि in the section 10.8 we have learned that certain amount of the heat energy transferred between the substance and its surrounding when it undergoes a change of the heat of state. The amount of the heat per unit mass transferred during the change of the state of the substance is called latent heat of the substance for the process. For example, if the heat is added to for a given quantity of ice at -10 degrees Celsius, the temperature of the ice increases until let's say the melting point 0 degrees Celsius. At this temperature, the addition of the more heat does not increase the temperature but cause the ice to melt or change its state. Once the entire ice melts, adding more heat will cause the temperature of the water to rise. A similar situation occurs during the liquid gas change of the state at the boiling water. Adding more heat to the boiling water causes the evaporation without increase in the temperature. अब यहाँ पर दिया हुआ है temperature of the change of state and the latent heat for the various substance in the 1 atm pressure. यहाँ पर melting point दिया हुआ है, यहाँ पर दिया हुआ LT boiling point और LT में दिया हुआ है। अब इसके बाद फिर आता है कि the heat required during a change of the state depends upon the heat of the transformation and the mass of the substance undergoing change of the state. Thus, if mass small amount of substance undergoes a change from the one state to another, then the quantity of the heat required is Q is equal to ml or L is equal to Q by m, where L is known as the latent heat and is a characteristic of the substance. With SI unit is joule per kg. The value of the L also depends upon the pressure. Its value is usually recorded at the standard atmospheric pressure. The latent heat of a solid liquid substance change is called the latent heat of the fusion, and that for a liquid gas state change is called the latent heat of the vaporization. These are often referred to as the heat of the fusion and the heat of the vaporization. A plot of the temperature versus heat for a quantity of the butter is shown in figure 10.12. The latent heat of the some substance, the freezing and the boiling point for given interval 10.5. यहाँ पर टेम्परेचर का दिया हुआ है, इधर दिया हुआ है हीट का। तो टेम्परेचर वर्सेस हीट फॉर द वाटर एट 1 atm pressure नॉट टू स्केल है जो दिखाया हुआ है। यहाँ पर फेज चेंज हो रहा है, फेज चेंज हो रहा है। फिर आता है कि नोट दैट when heat is added or removed during a change of the state, the temperature remains constant. Note in the figure 10.12 that the slopes of the phase lines are not all the same, which indicate the specific heat of the various states are not equal. For water, the latent heat of the fusion and the vaporization are LF is equal to 3.33 × 10⁵ joule per kg and L is equal to 22.6 × 10⁵ joule per kg respectively. That is 3.33 × 10⁵ joule of the heat needed to melt 1 kg of the ice at 0 degrees Celsius and 22.6 × 10⁵ joule of the heat needed to convert 1 kg of water into the steam at 4 degrees Celsius. So steam at the 4 degrees Celsius carries 22.6 × 10⁵ joule per kg more heat than the water at 4 degrees Celsius. This is why burns from the steam are more usually furious than from the boiling water. Next आता है कि when 0.15 kg of the ice at 0 degrees Celsius is mixed with 0.3 kg of the water at 0.50 degrees Celsius in a container, the resulting temperature is 6.7 degrees Celsius. तो calculate the heat of the fusion of the ice. इस वाटर दिया हुआ है 4085 जूल पर kg पर केल्विन। तो हीट लॉस का वाटर जो हो जाता है वो हो जाता है MFW थीटा एफ माइनस थीटा डब्ल्यू तो आ जाता है 554,376.1 जूल केल्विन। हीट रिक्वायर्ड टू मेल्ट आइस M2LF तो 0.15 kg LF हो जाता है। हीट रिक्वायर्ड टू राइज द टेम्परेचर ऑफ द आइस वाटर टू फाइनल टेम्परेचर होता है M1FW इक्वल टू थीटा फाइनल माइनस थीटा इनिशियल। तो हीट लॉस इक्वल टू होता है हीट गेनेड। अब यहाँ से अगर करेंगे तो आंसर आ गया 3.34 जूल पर kg पर केल्विन। नेक्स्ट अगला क्वेश्चन है कि कैलकुलेट द हीट रिक्वायर्ड टू कन्वर्ट द 3 kg ऑफ द आइस एट -12 डिग्री सेल्सियस केप्ट इन अ कैलोरीमीटर to steam at 4 degrees Celsius at atmospheric pressure. Given the specific heat capacity of the ice is 4 joule per kg per Kelvin, specific heat capacity of water 4186 joule per kg per Kelvin. Latent heat of fusion of ice दिया 3.35 × 10⁵ joule per kg और latent heat of steam दिया हुआ 2.256 × 10⁶ joule per kg. तो हम जानते हैं मास ऑफ द आइस हो जाता है 3 kg और स्पेसिफिक हीट कैपेसिटी हो जाता है 2100 जूल पर kg पर केल्विन और स्पेसिफिक हीट ऑफ कैपेसिटी ऑफ वाटर होता है 4185 जूल पर केजी पर केल्विन। तो लैटेंट हीट ऑफ फ्यूजन हो जाता है 3.35 × 5 जूल पर केजी और लैटेंट हीट ऑफ स्टीम हो जाता है 2.256 × 6 जूल पर केजी। Q इक्वल टू हो जाएगा हीट कन्वर्टेड टू required to convert 3 kg of the ice at -12 degrees Celsius to steam at 4 degrees Celsius. Q1 हो जाता है हीट रिक्वायर्ड टू कन्वर्ट ice at -12 degrees Celsius to ice at 0 degrees Celsius, यानी MA5 डेल्टा T1 तो आ जाएगा कितना 75,600 जूल। Q2 होता है हीट रिक्वायर्ड टू मेल्ट ice at 0 degrees Celsius to butter at 0 degrees Celsius, यानी इतना आ जाएगा। और Q3 निकालेंगे तो इतना आ रहा है, उसी तरह से Q4 निकालेंगे तो इतना आ रहा है। तो Q इक्वल टू हो जाएगा Q1 + Q2 + Q3 + Q4, यानी 9.1 × 10⁻⁶ जूल आ जाएगा। फिर आता है अगला टॉपिक है heat transfer. So we have seen that heat is energy transfer from the one system to another or from the one part of a system to another part arising due to temperature difference. What are the different ways by which this energy transfer take place? There are three distinct modes of the heat transfer: convection, convection and radiation. तो पहला आता है convection. तो convection is the mechanism of the transfer of the heat between the two adjacent parts of the body because of their temperature difference. Suppose one end of the metallic rod is put in the flame, the other end of the rod will soon be so hot that you cannot hold it by bare hands. Here heat transfer takes place by the connection from the hot end of the body to its different parts of the other end. Gases are the poor thermal conductors, while the liquids have conductivity intermediate between solid and gases. Heat conduction may be described quantitatively as the time rate of the heat flow in a material for a given temperature difference. Consider a metallic bar of the length L and a uniform cross-section with two ends maintained at a different temperature. This can be done, for example, by putting the ends in a thermal contact with large behavior at temperature T, Tc and Td respectively. Let us assume the ideal condition that the sides of the bar are fully insulated so that no heat exchange between the sides and the surrounding. After some time, the steady state is reached. The temperature of the bar decreases uniformly with the distance Tc to the Td, where Tc is greater than Tda. The reservoir at C supply the heat at a constant rate, which transfers through the bar and is given out of the same rate through a reservoir at D. It is found experimentally that this steady state, the rate of the flow of the heat or the heat current by H is proportional to the same temperature Tc minus Td and the area of cross section A, and is inversely proportional to the length L. So H is equal to K Tc minus Td by L. So steady straight heat flow by the connection in a bar with its two ends maintained at temperature Tc and Td. So Tc greater than होता है Td. The constant of proportionality K is called the thermal conductivity of the material. The greater the value of the K for a material, the more rapidly will it conduct heat. The SI unit of K is joule per second per meter per Kelvin or watt per meter per Kelvin. The thermal conductivity of the various substances are listed in table 10.6. These values are vary slightly with the temperature but can be considered to be the constant over a normal temperature range. फिर आता है compare the relatively large thermal conductivity of the good thermal conductors and materials with the relatively small thermal conductivity of some good thermal insulator, such as the wood and the glass wool. You may have noticed that some cooking pots have copper coating on the bottom. Being a good conductor of the heat, copper promotes the distribution of the heat over the bottom of a pot. For the uniform cooking, plastic foams, on the other hand, are good insulators, mainly because they contain pockets of the air. Recall that gases are poor conductors and note that low thermal conductivity of air in the table 10.5. Heat retention and transfer are important in many other applications. Houses made of the concrete roofs gets very hot during the summer days because thermal conductivity of the concrete, though much smaller than that of a metal, is still not small enough. Therefore, people usually prefer to give a layer of earth or foam insulation on the ceiling so that heat transfer is prohibited and keeps the room cooler. In some situations, the heat transfer is critical. In a nuclear reactor, for example, elaborate heat transfer systems need to be installed so that the enormous energy produced by the nuclear fusion in the core transit out sufficiently fast, thus preventing the core from the overheating. फिर यहाँ पर दिया हुआ है एक क्वेश्चन है मटेरियल, उसका थर्मल कंडक्टिविटी दिया हुआ है, तो मेटल्स का दिया हुआ है, मेटल्स का दिया हुआ है, नॉन मेटल्स का दिया हुआ है और गैसेज का दिया हुआ है. फिर इसके बाद आता है कि what is the temperature of the steel copper junction in the steady state of the system for the figure 10.15. Length of the steel rod 15 cm, length of the copper rod 10 cm, temperature of the furnace 10 degrees Celsius, temperature of the other end 0 degrees Celsius. The area of the cross section of the steel rod is twice that of the copper rod. Thermal conductivity of the steel है जो 15.2 जूल पर सेकंड मीटर पर केल्विन है, and of copper 385 जूल पर सेकंड पर मीटर पर केल्विन आता है. तो इसमें है कि the insulating material around the rods reduces the heat loss from the sides of the rod. Therefore, the heat flow only along the length of the rods. Consider any cross section of the rod. In the steady state, heat flowing into the element must equal the heat flowing out of it. Otherwise, there would be a net gain or the loss of the heat by the element, and this temperature would not be steady. Thus, in the steady state, Rate of the heat flowing across a cross-section of the rod is the same at every point along the length of the combined steel copper rod. Let T be the temperature of the steel rod junction at the steady state. Then the K1 A1 times minus T by L1 is equal to K2 A2 T minus 0 by L2, where 1 and 2 refer to the steel and the copper rod respectively. For the A1 is equal to 2 A1, A2 L1 is equal to 15 cm, L2 is equal to 10 cm, K1 is equal to 15.2, K2 is equal to 350 joule. So we have 15.2 गुना 2 300 T by 15 is equal to 350 T by 10, तो which gives T is equal to 44.4 degree Celsius. फिर आता है an iron bar Li is equal to 0.1, A1 is equal to 0.02 meter for K1 is equal to 29 watt per meter per Kelvin, and a brass bar L2 is equal to 0.1 meter, A2 is equal to 0.02 meter for, and K2 is equal to x0 watt per meter per Kelvin are folded into end as shown in figure 10.16. The free endings for the iron bar and the brass bar are maintained at 1043 Kelvin and 243 Kelvin respectively. Obtain the expression for and hence compute the temperature of the junctions of the two bars, the equivalent temporal conductivity of the compound bar, and the heat current through the compound bar. तो यहाँ से आता है कि लेट L1 इज इक्वल टू L2 इक्वल टू L इक्वल टू 0.1 मीटर, A1 इक्वल टू A2 इक्वल टू A इक्वल टू 0.02 मीटर स्क्वायर, K1 इक्वल टू 29 वाट पर मीटर पर केल्विन एंड K2 इक्वल टू 109 वाट per meter per Kelvin. T1 is equal to 373, T2 is equal to 273. So under the steady state condition, the heat current H through the bar is equal to the hot heat current H2 through the glass bar. So for H is equal to H1 is equal to H2. So K1 A1 T1 minus 0 by L1 is equal to K2 A2 T naught minus 0 by L2. So for the A1 is equal to A2 is equal to A, L1 is equal to L2 is equal to L. This figure lead to K1 T1 minus T naught is equal to K2 T naught minus T2. Thus the junction temperature T naught of the two bars T naught is equal to K1 T1 by K2 T2 by K1 plus K2. Using this equation, the heat current H through the either bar H is equal to K1A T1 minus T0 by L plus is equal to K2A T0 minus T2 by L. तो यहाँ से करेंगे K1 K2 by K1 plus K2 A T1 minus T0 by L यानी A T1 minus T2 by L 1 by K1 plus 1 by K2. तो आता है कि using this equation, the heat current H dash through the compound bar of the length L1 plus L2 is equal to 2L, and the equivalent thermoconductivity K dash of the compound bar are given by H dash is equal to K1A K dash A T1 minus T2 by 12H. So K dash is equal to K1 K2 by K1 plus K2, और T0 is equal to K1 T1 plus K2 T2 by K1 plus K2, और K dash is equal to K1 K2 by K1 plus K2 आ जाता है. और तीसरा में H dash is equal to K dash A T1 minus T2 by 12 ट्रांसफर करेंगे तो आएगा 16.1 वाट. फिर आता है कन्वेक्शन. तो इसमें है कि कन्वेक्शन इज मोड ऑफ द हीट ट्रांसफर बाय द एक्चुअल मोशन ऑफ द मैटर. It is possible only in the fluids. Convection can be natural or the forced. In the natural convection, gravity plays an important part. When a fluid is heated from below, the hot part expands and therefore it becomes less dense. Because of the buoyancy, it rises and the upper colder part displaces it. This again gets fitted, rises up and replaced by the relatively colder part of the fluid. The process goes on. This mode of the heat transfer is inherently different from the convection. Convection involves the bulk transfer of the different parts of the fluid. In forced convection, material is forced to move by a pump or by some other physical means. The common examples of the forced convection system are the forced air heating system in the home circulator system, and the cooling system of the automobile engine. In the human body, the heart acts as a pump that circulates the blood through the different parts of the body, transferring the heat by the forced convection and maintaining at a uniform temperature. Natural convection is responsible for the many familiar phenomena. In the day, the ground heats up more quickly than the larger body of the batter. This occurs both because batter has a greater specific heat capacity and because mixing current disperses the absorbed heat throughout the greater volume of the batter. The air in the contact with the warm ground is heated by the conduction. It expands, becoming less dense than the corresponding surrounding cooler air. As a result, the warm air rises in the currents and the other air moves bands to fill the space, creating a sea bridge near the large body of the batter. Cooler air defends when the thermal convection cycle is set up, which transfer heat energy heat away from the land. At night, the ground loses its heat more quickly and the water surface is warmer than the land. As a result, the cycle is reversed. फिर आता है the other example of the natural convection is the steady state surface wind on the water blowing it from the north east towards the equator, the so-called trade wind. A reasonable explanation is as follows. The equatorial and the polar region of the earth receive unequal solar heat. Air at Earth's surface near the equator is hot, while the air in the upper atmosphere of the poles is cold. In absence of any other factor, a convection current would be set up with the air at the equatorial surface rising and moving out towards the poles, defending and upstreaming it towards the equator. The rotation of the earth, however, modifies this convection current. Because of this, air closer to the equator has an eastward speed of the 12 km per hour, while it is zero close to the poles. As a result, the air defends not at the poles but at 30 north latitude and return to the equator. This is called the trade wind. फिर आता है रेडिएशन. तो conduction and convection require some material as a transport medium. These modes of the heat transport cannot operate between the bodies separated by a distance in the vacuum. But the earth did not receive heat from the sun across a huge distance. Similarly, we quickly feel the warmth of the fire nearby even though air conducts poorly and before convection takes some time to set in. The third mechanism for the heat transport need no medium. It is called a radiation, and the energy for transport by the electromagnetic wave is called the radiant energy. In electromagnetic wave, the electric and the magnetic fields oscillate in the space and time. Like any wave, electromagnetic waves can have different wavelength and can travel in the vacuum with the same speed, namely the speed of the light. That means 308 meters per second. You will learn these matters in the more detail, but you now know why heat transfer by the radiation does not need any medium and why it is so fast. This is how heat is transferred to the earth from the sun through the empty space. All bodies emit radiant energy, whether they are solid, liquid or gas. Electromagnetic radiation emitted by the body by the virtue of its temperature, like the radiation by a red hot iron or the light from a filament lamp, is called the thermal radiation. फिर आता है कि when this thermal radiation falls on the other body, it is partially reflected and partially absorbed. The amount of the heat that a body can absorb by the radiation depends upon the color of the body. We find that a black body absorb heat, absorb and emit radiant energy better than the body of the lighter color. This fact finds many applications in our daily life. We wear white or the light colored cloth in the summer so that they absorb the lift heat from the sun. However, during the winter, we use dark colored cloth which absorb heat from the sun and keep our body warm. The bottom of the utensils for cooking food are blackened so that they absorb the maximum heat from the fire and transport it to the vegetable to be cooked. Similarly, a dewar flask or the thermos bottom is a device to minimize the heat transfer between the content of the bottle and the outside. It consists of a double-bodied glass vessel with the window and the outer ball coated with the silver. Radiation from the inner balls is reflected back to the contents of the bottle. The outer ball simply reflects back any incoming radiation. The space between the walls is evacuated to reduce the conduction and convection loss, and the flask is supported on the insulator like cork. The device is therefore useful for preventing hot contents like the milk from getting cold, or alternatively to store the cold contents like ice. फिर आता black body radiation. So we have so far not mentioned the wavelength content of the thermal radiation. The important things about the thermal radiation at any temperature is that it is not of one or a few wavelengths but has a continuous spectrum from a small to the longer wavelength. The energy content of the radiation, however, varies for different wavelengths. Figure 10.1 it gives the experimental curve for the radiation energy per unit area per unit wavelength emitted by a black body versus wavelength for the different temperature. Energy emitted versus the wavelength for a black body at the different temperature. फिर इसके बाद आता है कि notice that the wavelength lambda m for which energy is the maximum decrease with increasing temperature. The relation between lambda m and lambda t is given by Martin on a Bn's displacement law. So lambda m into t is equal to the constant. The value of the constant, Bn's the constant is 2.9 minus 3 meter per Kelvin. This will explain why the color of the piece of the iron heated in a hot flame first become dull red, then a reddish yellow, and finally become hot. Bn's law is useful for estimating the surface temperature of the celestial bodies like the moon, sun, and other stars. Light from the moon is found to have a maximum intensity near the wavelength of 14 micrometer. By Bn's law, the surface of the moon is estimated to have a temperature of 200 Kelvin. Solar radiation has a maximum lambda 4753 Kelvin angstrom. This corresponds to that T is equal to 6060 Kelvin. Remember, this is the temperature of the surface of the sun, not in its interior. The most significant feature of the black body radiation curve in the figure 10.18 is that they are inversal. They depend only on the temperature and not on the size, shape, or the material of the black body. Attempts to explain the black body radiation theoretically at the beginning of the 20th century as per the quantum revolution in the physics, as you will learn in the later courses. Energy can be transferred by the radiation over the large distances without a medium, that means in the vacuum. The total electromagnetic energy radiated by a body at absolute temperature T is proportional to its size, its ability to radiate called emissivity, and most importantly, its to its temperature. For a body which is perfectly radiated, the energy emitted per unit time is given by H tag is equal to A sigma T के power 4. फिर आता है कि where A is the area, T is the absolute temperature of the body. This relation obtained experimentally by the Stephens and later proved theoretically by the Boltzmann in the Stephen-Boltzmann law, and the constant sigma is called the Stephen-Boltzmann constant. Its value in F 95.61 गुना 10⁻8 वाट per meter square per Kelvin के power 4 है. Most bodies emit only a fraction of the rate. A substance like the lamp black comes closer to the limit 1. Therefore, the dimensionless fraction E called the emissivity and rates is equal to A sigma T power 4, where E is equal to 1 for a perfect radiator. For a tungsten lamp of the water, for example, E is equal to 0.4. The tungsten lamp at a temperature of 10 Kelvin and a surface area of 0.3 meters square radiates at the rate of H equal to 0.3 गुना 10 का पावर माइनस 4 गुना 0.4 गुना 5.61 गुना 10 माइनस 8 गुना 3000 का पावर 4 इज इक्वल टू आएगा 50 वाट. A body at a temperature T with surrounding at a temperature Tf emits as well as receives energy. For a perfect radiator, the net rate of the loss of the radiant energy H equal to sigma at T का पावर 4 minus Tf का पावर 4. फिर आता है कि for a body with intensity E, the relation modified to H equal to E a sigma T का पावर 4 minus Tf का पावर 4. As an example, let us estimate the heat radiated by our body. Suppose the surface area of a person's body is about 1.9 meters square and the room temperature is 5 degrees Celsius. The internal body temperature, we know, is about 37 degrees Celsius. The skin temperature may be 28 degrees Celsius. The emissivity of the skin is about 0.987 for the relevant region of electromagnetic radiation. The heat rate of heat loss is H equal to 5.61 गुना 4 minus 8 गुना 1.9 गुना 0.97 गुना 3 1 के पावर 4 minus 295 के पावर 4 यानी 56.4 watt, which is more than half the rate of the energy production of the body at a rate 120 watt. To prevent this heat loss effectively, better than ordinary clothing, modern Arctic clothing has an additional thin, fine metallic layer next to the skin which reflects the body radiation. फिर आता है Newton's law of cooling. So we all know that hot butter or the milk, when left on the table, begins to cool gradually. Ultimately, it attains the temperature of the surrounding. To study how fast or slow a given body can cool on exchanging heat with the surrounding, let us perform the following activity. Take some butter, set in thermal in a calorimeter with a stirrer and cover it with a two-holed lid. Fix the stirrer through one hole and fix the thermometer through the another hole in the lid and make sure that the bowl of the thermometer is immersed in the water. Note the reading of the thermometer. The reading is T1 is the temperature of the surrounding. Heat the water kept in the calorimeter till the attains the temperature of 40 degrees Celsius above the room temperature. That means temperature of the surrounding. Then stop heating the water by removing the heat source of start the stopwatch and note the reading of the thermometer after a fixed interval of time. So after every 1 minute of stirring gently with the stirrer. Continue to note the temperature T2 of the water till it attains the temperature about 5 degrees Celsius above that of the surrounding. Then the plot a graph by taking the each value of the temperature delta T T2 minus T1 along the y-axis and the corresponding value of the T along the x-axis. The delta T by time minute the curve showing the cooling of the hot water with the time decay. From the graph you can infer how the cooling of the hot water depends on the difference of its temperature from that of the surrounding. You will also notice that initially the rate of the cooling is higher and decreases as the temperature of the body falls. The activity shows that a hot body loses heat to its surrounding in the form of the heat radiation. The rate of the loss of the heat depends upon the difference in the temperature between the body and its surrounding. Newton by the first to study in a systematic manner the relation between the heat lost by the body in a given enclosure and its temperature. According to Newton's law of the cooling, the rate of the heat loss minus dq by dt of the body is directly proportional to the difference of the temperature delta T equal to T2 minus T1 of the body and the surrounding. The law holds only for the small difference of the temperature, as the loss of the heat by the radiation depends upon the nature of the substance of the body and the area of the exposed surface. We can write minus dq by dt equal to k T2 minus T1, where k is the positive constant depending upon the area and the nature of the body of the nature of the surface of the body. Suppose a body of the mass m and the specific heat capacity F is a temperature T2. Let T1 be the temperature of the surrounding. If the temperature falls on a small amount dt2 in the time dt, then the amount of the heat lost dq equal to mf dt2. Rate of loss of heat given by dq by dt equal to mf dt2 by dt. फिर यहाँ पर आता है from the equation 10.15 and the 10.16 we have minus mf dt2 by dt equal to k t2 minus t1 यानी dt2 by t2 minus t1 equal to minus k by mf dt यानी minus k dt, where k is equal to mf. On integrating log e t2 minus t1 is equal to minus kt plus c, where t2 equal to t1 plus c dash e minus kt, so where c dash equal to e to the power of c. Equation 10.23 enable you to calculate the time of the cooling of a body through a particular range of the temperature. For small temperature difference, the rate of the cooling due to the conduction, convection and radiation combined is proportional to the difference in the temperature. It is valid approximately in the transfer of the heat from a radiator to the room, the loss of the heat through the wall of the room, or the cooling of a cup of tea on the table. फिर यहाँ पर दिए हुए वेरिफिकेशन ऑफ द न्यूटन लॉज ऑफ द कूलिंग दिया हुआ है log T2 minus T1 और यहाँ पर दिया हुआ T2. Newton's law of cooling can be verified with the help of the experimental setup shown in the figure 10.2a. The setup consists of the double-walled vessel containing water between the two balls, a copper calorimeter C containing the hot hot butter is placed inside the double-barreled vessel. The two thermometers through the cork are used to note the temperature T2 of the butter in the calorimeter and the T1 of the hot butter between the double balls respectively. Temperature of the hot butter in the calorimeter is noted after equal intervals of time. A graph is plotted between the log E T2 minus T1 or ln T2 minus T1 and the time. The nature of the graph is observed to the straight line having the negative slope as shown in the figure 10.20b. This is the support of a given 10.22. अगला क्वेश्चन कि pan filled with the hot food cools from 94 degrees Celsius to 86 degrees Celsius in the 2 minutes. When the temperature is at 20 degrees Celsius, how long will it take to cool from 71 degrees Celsius to 59 degrees Celsius? So the average temperature of the 94 degrees Celsius and 86 degrees Celsius is 90 degrees Celsius, which is 40 degrees Celsius above the room temperature. Under this condition, the pan cools 80 degrees Celsius to 2 minutes. Using the given 10.21, we have change in temperature by time is equal to K delta T. So 8 degrees Celsius by 2 minutes equal to K 40 degrees Celsius. The average of the 59 and the 21 degrees Celsius is the 20 degrees Celsius, which is the 50 degrees Celsius of room temperature. K is the same for this situation as for the original. So 2 degrees Celsius by time is equal to K into 50 degrees Celsius. When we divide above the two equation, we have K by 2 C by time is equal to K by 40 by K by 50. Therefore time is equal to 0.1 minute is equal to 42 सेकंड. अब इसका समरी है कि हीट इज अ फॉर्म ऑफ द एनर्जी दैट फ्लो बिटवीन द बॉडी एंड द सराउंडिंग मीडियम बाय द वर्च्यू ऑफ द टेम्परेचर डिफरेंस बिटवीन देम. द डिग्री ऑफ द हॉटनेस ऑफ द बॉडी इज कॉल्ड क्वांटिटेटिवली रिप्रेजेंटेड बाय द टेम्परेचर. A temperature measuring the device thermometer make use of some measurable property called the thermometric property that change with the temperature. Different thermometers lead to the different temperature scale. To construct a thermometer scale, two fixed points are chosen and assigned some arbitrary value of the temperature. The two numbers fix the origin of the scale and the size of the unit. The Celsius temperature and the Fahrenheit temperature are dated at Tf equal to 9 by Tc plus 32. The ideal gas equation connecting the pressure, volume and the fluid temperature is Pv is equal to mu RT, where mu is the number of the moles and R is the universal gas constant. In the absolute temperature scale, the zero of the scale corresponds to the temperature where every substance in the nature has the least molecular activity. The Kelvin absolute temperature has the same unit size as the Celsius scale but differs in the origin. So Tc equal to T minus the 47.85. The coefficient of the linear expansion and the volume expansion are defined by the relation delta L by L is equal to alpha delta T और delta V by V is equal to alpha V delta T. फिर आता है कि where delta L and delta V do not change in the length and the volume for a change of the temperature delta T, this relation between them is alpha V is equal to 3 alpha 1 or the specific capacity of a substance defined by F equal to 1 by m delta Q by delta T, where m is the mass of the substance and delta Q is the heat required to change the temperature by delta T. The molar specific heat capacity of a substance is defined by C equal to 1 by mu delta Q by delta T, where mu is the number of the moles of the substance. The latent heat of the fusion Lf in the water per unit mass required to change substance from the fluid into the liquid at the same temperature and the pressure. The latent heat of the vaporization Lv is the heat per unit mass required to change the substance from the liquid to the vapor state without changing the temperature and pressure. The three modes of the heat transfer are the conduction, convection and the radiation. In the conduction, heat is transferred between the neighboring part of the body through the molecular collision without any flow of the matter. For a bar of the length L and the uniform cross-section A with the ends maintained at a temperature Tc and Td, the rate of the flow of the heat is equal to K Tc minus Td by L, where K the thermal conductivity of the material of the bar. इसके आगे फिर आता है कि न्यूटन्स लॉ ऑफ द कूलिंग से दैट द रेट ऑफ द कूलिंग ऑफ द बॉडी प्रोपोर्शनल टू द एक्सेस टेम्परेचर ऑफ द बॉडी ओवर द सराउंडिंग, यानी डी क्यू बाई डी टी इक्वल टू माइनस के T2 minus T1, but T1 is the temperature of the surrounding and T2 is the temperature of the body. फिर आता है कि अमाउंट ऑफ सब्सटेंस म्यू का मोल होता है, सेल्सियस टेम्परेचर का होता है के, केल्विन ऑफ फ्लूइड टेम्परेचर का होता है केल्विन और T इक्वल टू T माइनस 273.15. कोफिशिएंट ऑफ लिनियर एक्सपेंशन अल्फा का होता है K माइनस 1. कोफिशिएंट ऑफ वॉल्यूम एक्सपेंशन अल्फा 2 इक्वल टू K माइनस 1 is equal to 3 alpha 1. Heat supplied with the system delta Q equal to ml2 T minus 2. Q is not a state variable. फिर आता है specific capacity K equal to L2 T minus 2 K minus 1 joule per kg per Kelvin और thermal conductivity K equal to ml T minus K3 K minus 1 joule per second per Kelvin और H equal to minus Ka dt by dx हो जाता है. फिर आता है इसमें कुछ क्वेश्चन है कि the relation connecting the Kelvin and the Celsius temperature T equal to Tc plus 273.15 होता है and the assignment T equal to 273.15 for the triple point of the butter are exact relation by choice. With this choice, the Celsius temperature of the melting point of the butter and the boiling point of the butter both one atmosphere are very close but not exactly equal to 0 degrees Celsius and 4 degrees Celsius respectively. In the original Celsius scale, the latter fixed point were exactly 0 degrees Celsius and 4 degrees Celsius by choice, but not the triple point of the butter is the preferred choice for the fixed point because it has a unique temperature. A liquid in equilibrium with the butter with the vapor has the same pressure and the temperature throughout the system. The two phases in equilibrium differ in their molar volume density. This is true for a system with any number of the phases in equilibrium. Heat transfer always involves temperature difference between the two systems or the two parts of the same system. Any energy transfer that not involve the temperature difference is in some way is not heat. Convection involves flow of the matter between a fluid due to the unequal temperature of its part. A hot bar placed under running a tap loses heat by the convection between the surface of the bar and the butter and not by the convection between the butter. तो यहाँ पे इसका एनसीईआरटी कंप्लीट होता है। इसका क्वेश्चन के सॉल्यूशन है जो ऐसे नहीं देख रहे हैं क्योंकि थोड़ा सा जो प्रॉब्लम है क्वेश्चन वाइज ये देखना पड़ेगा, थोड़ा सा ज़्यादा क्वेश्चन भी है तो इसको है जो ऐसा देख कर है जो इसको देख सकते हैं। ये इसका ये हो गया, क्वेश्चन हो गए। और ये इसके क्वेश्चन के हो गया सॉल्यूशंस।